Long time no see. Long time no see.
Okay, are we all here?
Yes.
So?
No, it misses Jacques and Christophe, it seems.
Yes.
Yes, Christophe said he's coming, and Jack also. Thank you very much.
Okay, are we all here?
Yes.
I see Christophe and Jacques. Has he joined us or?
Yeah, Jack is coming.
Il faut que tu... Ouais. Yeah, Jack is also here, so
Yes,
I think
Guillaume. Okay.
just one second. I think yes, I think Jack. Okay. Oui.
C'est sur le clavier, pas sûr, c'est la Oui, Marianne, on va pouvoir commencer.
Okay, I can't see Jacques. He's there, isn't he?
Je suis dans la pièce.
Ah, okay, tu es. Okay, perfect.
Problem
Thank you.
Wi-Fi, and so you can start. I see the slides and everything with Christophe.
Okay, great. Shall I speak in English? Yes.
Yeah, sure.
Yes.
Okay.
Thank you very much.
Yes. Okay. So, Mr. Armando Carusone, you are invited to present the works carried out in your thesis during 3/4 of hour on the subject flow control over an airfoil, physical analysis of transient phenomena to improve performance and maneuverability. And the thesis has been directed by Jacques Borret and co-directed by Christophe Sicot in P Prime Institute. So you are invited to start the presentation, your defense.
Thank you very much, Professor Braza. So I will share my PowerPoint presentation just now. Okay, can you confirm the translation is okay for you?
Yeah, for me it's okay.
Okay,
I can see it.
thank you very much. Just 1 second.
I suggest during the defense to cut off the micros maybe and to reactivate them when we have to speak.
Yes, it's fine. Yes, it's fine.
Okay, I will do so. Also my camera.
Okay. Okay. So
Please go ahead.
thank you very much. So thank you very much, first of all, the members of the jury for participating in my presentation. So I will present my work on flow control over an airfoil that I've carried out at Institute P' with the financial support of DGA and ISE-ENSMA. I also want to thank my advisors, Professor Christophe Sicot, Professor Jacques Boré, and Professor Jean-Paul Bonnet, for their really good advice and insightful suggestions during my work. So I will present, first of all, the context and motivation of this work. From this video, in this presentation, you see that in some situations, unsteady load fluctuation may arise from random flow conditions such as gust or rapid maneuver. And flow control is a valid tool that may be used to alleviate the unsteady loads generated in this complex situation, among other tools that are widely used. However, in order to improve the control effectiveness, it's first of all fundamental to understand and master the transient effects induced by actuation. And so this is the main objective and the core of this thesis. In particular, we will start to investigate the effects of the flow control over the airfoil and if it's effective even with large-scale separated regions. Then we will go into the second part of this work and we will investigate the transient effects induced by actuation, which is, as I said before, the main objective of this work, and with the objective of improving the control effectiveness, or in other words, we will see to increase the rate of loads variation, and with the perspectives of giving useful insights toward the development of control strategies that can be used in real unsteady situations. So first of all, I will present the background of this work. Then I will give some details of the experimental setup that has been used to carry out the experiments, and then I will talk about the results. In particular, I will present first of all the baseline flow configuration over the airfoil, and then the time averaged effects of the control. Then we will go into the main part of this presentation that is about the transient effects induced by actuation. So let's now talk about the background. We all know that airfoils at high incidence angle can experience flow separation. As you can see from in this picture, where you see this picture was obtained by Bourgois in 2006 in the same laboratory, so at Institute P', using laser visualization. And we see that if actuation is applied from an appropriate location upstream of the separation, it's able to suppress or reduce flow separation. In particular, this flow attachment can induce very beneficial effects on the performance of the airfoil. Indeed, it can increase the lift, reduce the drag, or postpone the stall angle. As we can see from this picture here, where we see the variation of the lift with the incidence angle. In particular, this picture was obtained by Xiao under the direction of Professor Bonnet in 2008, and we see that if the actuation is applied, in this case from 30% of the chord, we are able to increase the maximum lift, but even the post-stall lift. However, in real conditions, the flow field may be highly unsteady, and so the previous quasi-steady prediction may be no longer useful. As you can see in these cases, where I present several situations where the airfoil experiences unsteady loads. For example, in the case of wind turbines, or even when the airfoil experiences longitudinal gust, or in the case of an helicopter rotor, when the airfoil experiences dynamic stall. And in this case, control is used in an unsteady manner in order to alleviate the unsteady loads generated in these phases. So, flow control, we have seen that flow control may be exploited to alleviate unsteady loads in these cases. And so we need to exploit the transient effects of actuation to improve the control authority. And for this reason, it's first of all necessary to investigate the transient phenomena induced by actuation. And this is the main objective of this work, as I said before. For this reason, many authors in the last years have investigated the effects of the actuation onset removal. For example, I mention here the work of Amitai and Professor Gleiser, where they investigated the transient effects induced after the actuation onset removal. In particular, in this picture, I present the variation of the circulation around the airfoil in function of the normalized time T+. In particular, the normalized time is basically the time, the ratio between the time in second and the convective time over the airfoil. So you see that strong transients are found immediately after the actuation onset removal, and in particular, these transient effects were associated to the sharding or large-scale vorticity concentration of alternate sands. Another particular case that was very useful to understand the transient effects of the actuation is the case of the single pulse actuation, which has a characteristic time scale very short compared to the convective time over the airfoil. And also in this case, you see that the single pulse actuation can induce a very strong circulation fluctuation around the airfoil that corresponds also to a lift fluctuation. And in particular, the maximum lift value is obtained after about 2 convective time scales. This time scale is quite short, but can be very long if the control is intended to control unsteady loads over the airfoil that can have characteristic time scales even shorter than the convective time over the airfoil. For this reason, we asked if it's possible to enhance the control effectiveness by reducing the time to attaining the maximum lift. Or in other words, we try to increase the rate of variation of the aerodynamic loads. And this is the main objective of this work. But let's first of all analyze the experimental setup that we used to perform the experiments. So the experiments are performed in the subsonic wind tunnel of Enzma using a NACA 15 airfoil model, having a chord of 35 centimeters and a Reynolds number of about 500,000. In particular, the transition is triggered at the leading edge in order to obtain a fully turbulent flow field along the chord. The airfoil is mounted between 2 rotating discs that allow to change the incidence, and end plates are used to limit the interaction between the wall boundary layer and the surface of the airfoil. With this setup, we are able to increase the effective aspect ratio of the airfoil and to produce a 2-dimensional flow distribution along the span. The actuation instead is performed using 44 pulsed vortex generator jets that are embedded 30% of the chord and are inclined with a yaw angle of 60 degrees and a pitch angle of 30 degrees. They are able to produce streamwise vortices, as you can see here, downstream, that enhance the mixing between the outer and the inner layer of the boundary layer and promote flow reattachment. This setup in particular has been chosen from the literature because it allows for the maximum streamwise accumulation downstream of streamwise vorticity accumulation downstream of the orifice. So the performance of the actuators instead are measured using hot wire anemometry, very close to the jet exit orifice. And here you can see the actuation response to several control laws. In particular, you see the response to single pulse control and to periodic control. You see that the response delay is very short, and in particular in these experiments, a maximum jet velocity of 5 times the free stream velocity has been chosen because it was able to completely reattach the flow even at larger scale in configuration, at high incidence with large scale separated regions. And with this maximum velocity, we were able to measure the performance of the actuation using the jet momentum coefficient, which is the ratio between the momentum flow rate of the jet actuation system and the momentum flow rate of the free stream. And in this setup, it has been about equal to 0.304%, so it's very low. To explore the transient phenomena induced by actuation, instead, we performed unsteady static pressure measurements and flow measurements using PIV, both synchronized and phase-locked to the actuation trigger signal. In particular, it's here important to know that all the PIV measurements that I will present later are phased averaged based on 300 images in order to reduce the uncertainty. So let's now go into the results. But first of all, I want to make a small premise before presenting the baseline flow configuration around the airfoil. In particular, we know that the airfoil, the flow in the wind tunnel is horizontal, so the free stream is parallel to the ground, and the airfoil rotates to create an incidence angle. But in this presentation, I always will rotate the frames in order to have the chord always horizontal for sake of simplicity of representation. So with this in mind, we can now analyze the streamwise velocity distribution around the airfoil, and in particular, we see that for incidents below 11 degrees, the flow is fully attached, while a partially separated region appears for incidences above 12 degrees, and it reaches 75% of the chord at 16 degrees. For this reason, it seems reasonable to place the actuators at 30% of the chord, in order to be upstream of the separated region even for 14 or 15 degrees. So let's now analyze the time averaged effects of the control, which is the starting point of our investigation. In particular, we notice here the variation of the lift in function of the incidence angle for several actuation laws. In particular, we applied both periodic control and steady blowing in red, and we see that actually the actuation is able to increase the lift for incidence above 8 degrees, as you can see from the picture below, presenting the percentage variation of the lift. In particular, the stall angles is also postponed from 13 degrees in the baseline configuration to 16 degrees in the controlled configuration. And the highest increase of lift is obtained at 16 degrees because we are able to reattach a very large scale separated region, allowing to strongly change the aerodynamic camber of the airfoil. But not only the lift is affected by the actuation, but also the drag, which is the pressure drag in this case, which is remarkably changed above 8 degrees as before, but it's interesting to notice that in this case we have a pressure drag increase for incidences above 14.5, while a pressure drag increase for incidents below 14.5 and a pressure drag decrease for incidents above 14.5. So let's explain this behavior by analyzing the pressure distribution around the airfoil at 14 and 16 degrees. In particular, we see here there is a big difference in the pressure distribution around the airfoil. In particular, we see that there is a very strong suction near the leading edge in the case of 16 degrees, because we have seen before that in this situation we are able to reattach a very large scale separated region, and so the change of aerodynamic camber that we obtain is able to increase the suction near the leading edge. This action actually results in pulling the airfoil in the upstream direction and corresponds to a drag decrease. In the case of 14 degrees, instead, we obtain a drag increase because the predominant effect of the actuation is a suction near the half chord, which actually pulls the airfoil in the downstream direction, increasing the drag. But the variation but not only the lift and the drag are affected by actuation, but also the maneuverability. Indeed, we see here the variation of the pitching moment coefficient, which is measured with respect to the quarter chord, with the incidence angle, and we see that there is a remarkable moment variation for incidents above 8 degrees, and there is a pitching moment degrees for incidents below 14.5, while the opposite for incidents above 14.5. To explain this phenomenon, we need to analyze the variation of the center of pressure induced by actuation. In particular, we see that, let's remember first of all what is the center of pressure. The center of pressure is the point where the resultant of the aerodynamic force is applied. So, since the moment is measured compared to the quarter chord and is positive in the pitch up sense, if the center of pressure moves downstream, it means that the moment is decreasing. And indeed, we see here for incidents below 14.5. while for incidents above 14.5, the pitching moment is decreasing because the center of pressure is moving upstream in the upstream direction. We can visualize this by analyzing again the distribution of the pressure around the airfoil for these two incidences, and we see that at 14 degrees the center of pressure moves downstream because of the suction near the alpha chord, which actually push the center of pressure downstreams, while for 16 degrees the strongest suction near the leading edge is able to change the center of pressure, moving it upstream, which corresponds to a moment increase. So another important feature that we can notice from this picture is that there is the postponement of a strong nose-down pitching moment from 13 degrees in the baseline configuration to 16 degrees in the actuated configuration. And this actually corresponds to postpone the stall angle of the airfoil. And so we actually are proving what we already observed with the lift coefficient, also with this curve. So in this first part of the presentation, we have analyzed the time average effects of the actuation. And in particular, we have seen that the actuation is able to increase the lift and reduce the drag for high incidence, which corresponds to beneficial effects for the efficiency, but also affect the maneuverability of the airfoil. Indeed, we have seen that actuation have a very strong influence on the pitching moment. Let's now go instead into the main part of this work, because the understanding of the time averaged control effect is very important, but is very common in the literature, and it's not the main objective of this work. But we will focus in the next, or in the following of this presentation, instead of the transient effects induced by actuation. So let's now investigate the transient effects of actuation, and let's try to answer to our previous question: if it's possible to enhance the effectiveness of the actuation using a fine-tuned control. For this reason, we test many actuation durations, in particular many single pulse actuation durations, compared with the steady blowing onset. In particular, we test this configuration both over attached and partially separated flow fields, but for sake of simplicity, I will only present the case of a partially separated case at 14 degrees, where the separation starts from mid-chord because it's the most representative case. What is the result? The result can be seen by analyzing the evolution of the lift coefficient in function of the normalized time t+. In particular, we see that the single pulse actuation induces a very different lift response compared to the steady blowing. This can be also seen by analyzing the derivative of the lift coefficient in function of the normalized time t+. And we see that the single pulse actuation increases the maximum rate of lift variation compared to the steady blowing. However, this is not only for delta t plus 0.29 that we show here, but it also happens for other duration of the actuation up to delta t plus 1.14, where we see that the difference between the single pulse and steady blowing is very small. So we can also notice from this picture that the maximum rate of lift variation is obtained for an incidence of about a pulse duration of about 0.5, in particular for delta t plus 0.46. This can be also understood by analyzing this other image, which represents the variation of the maximum derivative of the lift coefficient in function of the duration of the actuation. And we see that for 14 degrees, the maximum rate is obtained for delta t plus 0.46. This is also the case for other partially separated flow fields for incidents above 12 degrees, while a different behavior is found for 16 degrees, where indeed the actuation is applied from inside the separated region, and so it induces a different flow dynamics. For this reason, we cannot clearly evidence the maximum, while for other partially separated configuration, we can see that the maximum is obtained for an actuation duration of about delta t plus equal to 0.5. For attached airfoils, instead, the flow, the maximum derivative is only slightly affected by the pulse duration, and for this reason, we will not go into details of this case, but you can find all the more details in my PhD dissertation. So let's consider the case of 14 degrees being the most representative, and let's try to explain what is the physical mechanism responsible for the improvement of the rate. First of all, to explain this, we need to compare the single pulse actuation of delta t plus 0.46 and the steady actuation, to explain what is the dynamic, what is why the response of the flow is so different between these two cases, and then we will also try to explain what is the physical mechanism that leads to maximizing the rates of lift increase. For this reason, we compare the single pulse actuation of 0.46 with a longer and a shorter duration. So let's talk about the first step. So we compare in this following this presentation the case of delta t plus 0.46 and the steady blowing. In particular, it's important to notice that not only the lift coefficient is affected by the single pulse actuation, but also the pressure drag and the pitching moment, which are affected even more strongly than the lift. However, we will talk about the lift coefficient for sake of simplicity, and we will try to explain, as I said before, the physical mechanism responsible for the improvement of the rate. We can explain this by analyzing the evolution of the flow field over the airfoil that is represented here as the distribution of the span-wise vorticity concentration over the airfoil. In particular, you see that in the baseline configuration, the flow is separated from half chord, and a negative layer of vorticity is detached from the airfoil from half chord, and this is the signature of the separated shear layer. If I play now the video, you see that after the actuation onset, the separated shear layer is shed downstream, while upstream the flow becomes fully reattached over the airfoil as a consequence of the single pulse actuation. If now compare this flow response to the case of the single pulse, we can notice very different behaviors. Indeed, in the case of the single pulse actuation, we notice the formation of an unsteady separation bubble near the half chord, which moves downstream up to reach the trailing edge, and then it opens. So we can now explain what is the effect of this bubble on the lift evolution. For this reason, I put on the right of this figure, of this video, the evolution of the lift and of the derivative of the lift that I showed before. If I play the video again, we see that at the same phase when the bubble is created, we also increase the rate of the lift compared to the steady blowing. So it seems there is a very strong correlation between the formation of this bubble and the increase of the rate of lift variation. And so we want to understand why this bubble induces this strong increase of the rate. For this reason, we analyze the pressure distribution over the airfoil at for example, at an instant of time when the maximum is obtained. Remembering that in the case of the single pulse, we obtain the formation of the bubble. If now I look at the phase averaged pressure variation over the suction surface of the airfoil, which is compared to the baseline value, Cp0. So Cp minus Cp0 is basically the difference between the the phase averaged pressure at this phase and the baseline value, both for single pulse in red and steady blowing in black. In particular, you see that just upstream and downstream of the separation bubble, very small differences are found between these two cases. However, a very strong difference is found just below this bubble, where we find a really big unsteady, negative unsteady pressure variation that actually allows to improve the lift, and so, by consequence, the rate of lift variation. So we have understood that the bubble has a very big effect on the lift evolution. But however, to characterize the dynamical evolution of the flow field, we need to follow the progression and evolution of this unsteady separation bubble. In other words, we need to detect the instantaneous position of the reattachment point downstream of the bubble, which is represented in the case of streamlines as a moving saddle point. However, it's important to notice that we cannot use the interpretation which is given by streamlines, because streamlines are calculated in an Eulerian field, an Eulerian perspective. That means that they are calculated with a reference system which is fixed with the airfoil. And so in an unsteady case, they can really diverge from the actual particle trajectories. And so they are not representative of the real transport behavior over the airfoil. For this reason, we need to analyze the flow field with the Lagrangian perspective, That means we need to use a reference system which is fixed with the saddle point, which is moving with the saddle point. In this case, the reference system in green. And for this reason, we use the Lagrangian tool. That is the finite-time Lyapunov exponent that allows to track the region of maximum stretching between nearby trajectories after a finite time t. In particular, the FTLE is Galilean invariant and so is very well suited to our unsteady situation. Let's give a brief introduction to the FTLE, in particular if we consider the advection of a grid of particles using forward integration from time t0 to time t0 plus t. And if we consider that phi is the flow map that tracks the movement of this particle, we can calculate the spatial gradient, for example by central differencing of the flow map. It's very well known from the literature that the maximum stretching between nearby trajectories occurs in the unit direction associated with the largest eigenvalue of the matrix A, that we call, for example, lambda max. With this in mind, we can now define the FTLE as the product of the square root of lambda max for 1 over the integration time t. In particular, the FTLE sigma is calculated in this case in every point in the PIV domain at every instant of time. And you can see and the FTLE in particular provides the maximum exponential divergence over a finite time interval, t0, t0 plus t. So if we are able to calculate the FTLE value in every point of our PIV field, we can detect the ridges of the FTLE field that is represented here, for example, in red. And these ridges, the intersection between this ridge and the surface of the airfoil gives the instantaneous position of the attachment point in a Lagrangian perspective. In our study, in particular, we calculated the FTLE using phase averaged PIV fields based on 300 images each, and the time step to compute the particle trajectory has been chosen 0.25 millisecond, and the flow is affected using the Runge-Kutta fourth order algorithm. In particular, an integration time of 25 milliseconds is used to calculate the FTLE because it was enough to clearly reveal the unsteady topological evolution of the flow field. Moreover, the flow very close to the airfoil surface is not very well resolved by PIV because of laser light reflection, and so we approximated the flow near the wall using a sleep boundary condition. And so what is the result of the FTLE? The results of the FTLE can be seen here as, for example, I present here for the generic instant of time t plus 1.64. From this contour of the FTLE, you can really see the red line, which represents, as I said before, the region of maximum stretching between trajectories, that you can clearly see if I filter the image using a cutoff value of 80% of the max. And you see clearly the value of the FTLE maximum. You see here this red line that unambiguously reveals the position of the attachment point over the airfoil. In particular, the reattachment point over the airfoil is calculated on a line very close to the airfoil surface and very close to the region resolved by PIV, with a spatial resolution of about 0.2% of the chord. Let's now go into details of our calculation that I present here by looking at this video. In particular, you see that actually we can really follow the evolution of the bubble and the progression of the attachment point downstream of the bubble. This can also be seen by plotting some frames that I extracted from this video on the right, and in particular you see that the point is moving toward the trailing edge. The attachment point downstream of the bubble is moving toward the trailing edge, and we can track the progression of this point in function of the normalized time, as I did in this picture that on the x-axis presents the instantaneous position of the attachment point, and on the y-axis we have the normalized time t plus. So we see that this point is moving downstream with a velocity which is about equal to 20% of the free stream velocity, and at t plus about equal to 2 it reaches the trailing edge. It's not a coincidence that at this instant we also obtain the maximum value of the lift. Indeed, we can remember that this bubble is responsible for a negative unsteady pressure over the suction surface. When this bubble reaches the trailing edge, also this negative region of pressure extends all over the suction surface of the airfoil, providing the maximum lift. But after this phase, this bubble opens, and the flow starts to relax to the baseline state. And so for this reason, the load starts to decrease to the baseline value. So, however, it's important to state here that although I just talked about the flow dynamics on the suction surface of the airfoil, the flow evolution is rather global. This can be seen from this video that presents the response of the flow to the single pulse actuation. And in particular, we see that also the streamlines in the near wake are affected by the actuation, not only the flow field over the suction surface of the airfoil. In particular, we can take, we can say, a snapshot of this video and analyze the streamlines distribution at this phase. For example, let's consider the case at t plus 2.04. If I trace here schematics of the streamlines at this phase, and we see the concomitant presence of the separation bubble near the trailing edge and the shedding of positive vorticity in the near wake, which is associated with the increase of lift. And in particular, we see that the streamlines near the trailing edge in the near wake are deviated in the downward direction. This actually corresponds to a fluidic flap effect that induce a global flow response around the airfoil. This can be seen by analyzing the pressure evolution in a point very close to the trailing edge on the pressure surface of the airfoil. And in particular, we see that it's very interesting because we see that the pressure evolution in these points really follows the global lift evolution around the airfoil. However, to take into account the integrated effect of all the pressure over the airfoil, we split the contribution to the derivative of the lift coefficient into two components. The components corresponding to the suction surface and the component corresponding to the pressure surface of the airfoil. And you see that in both situations, both suction and pressure surface contribute to the improvement of the rate of lift increase. And so the phenomenon is global. So in this second part, we have seen that we have compared the transient effects induced by single pulse actuation and steady blowing. We have seen that the single pulse actuation is able to enhance the rate of variation of the lift, or in a general of the aerodynamic loads, compared to the steady actuation. And in particular, we have seen that this improvement is due to the control of the formation of an unsteady separated region that modifies the instantaneous virtual shape over the airfoil. Let's now go into the third part of this presentation, and because I've said before that after we understood what is the physical mechanism leading to increase the lift rate, we now want to understand what is the mechanism leading to maximizing the rate of variation of the loads. For this reason, to unveil the transient phenomena responsible for this enhancement, we compare the effects of delta t plus 0.46 with a shorter and a longer pulse duration, in particular 0.29 and 0.86. This can be analyzed in this video, which is exactly the same video as before. But on the left, I present three durations of the actuation, so 0.29, 0.46, and 0.86. And on the right, I present the corresponding evolution of the lift and of the derivative of the lift coefficient. I made a small zoom from 0 to 4, so just to better better evidence the load variation. So if I play now the video, we see that in a first phase after the actuation onset, the flow response is very similar for the three cases. And so this corresponds to very similar loads evolution, as you can see here. However, if I go at an instant of time after, we see that in the case of the shorter actuation, we have the formation of a separation bubble because the actuation is switched off earlier. And this corresponds to, we have seen before, to an increase in lift. Indeed, if we go to analyze the loads in the zoom that I present here, we see that in the case of the 0.29, so the blue one, the minimum lift is a bit higher. So this bubble is already having its effect. If I go on with the video, we see the most striking feature. In particular, we see that for both 029 and 046, we obtain the formation of a bubble, while for 086, we have no bubble at all, and the flow is fully reattached. And so this corresponds to a lower rate of lift increase compared to the shorter actuation duration, because we have seen that the bubble, since the bubble is responsible for the increase of the rate of the lift, since we have no bubble, we expect a lower rate. However, if I go on with the video, we see that actually this bubble is formed also for the case of delta t plus 086, but is formed too late and very close to the phase when the maximum lift is obtained. And for this reason, this bubble is expected to be less effective in enhancing the rate of lift variation. So, if I go now from the beginning of the video, we can see and we can conclude that for both 029 and 046, we obtain the formation of a separation bubble, while we have no formation of the bubble for 086 for the longer actuation direction, which explains why we have a lower rate of lift increase. However, it's still strange that for both 029 and 046 we have the formation of the bubble, but we find very different loads in these two cases, very different rates in these two cases. In particular, 046 induces higher rate compared to 029. So we want to explain this by analyzing, in this case, the evolution of the separation bubble using our dear friend, the FTLE tool. In this case, we take an instant of time at, for example, t plus 1.5, and we compare the FTLE fields for these two cases. In particular, since this actuation is switched off earlier for 029, also the bubble is formed earlier. So it's expected, and is proved by this picture, that the reattachment point, the stream of the bubble, is closer to the trailing edge in the case of the shorter actuation duration, so it's downstream compared to delta t plus 046, as you can see here. But however, this is a static vision and does not allow to explain why the rate of loads variation are so different, because to explain this we need to understand the evolution of this bubble in these two cases. And for this reason I used another time a video of comparison between these two cases. If I play the video, it's not very clear, but we have the impression that the bubble travels faster for the case of 0.46, so the red one. This is proved by analyzing the evolution of the attachment point for these two cases. In particular, you see that the red line that corresponds to 0.46 corresponds to a faster movement of the attachment point downstream of the bubble compared to the blue one, so 0.29. And in particular, we see that the velocity in the case of 0.46 is 20% of the free stream velocity, while for 0.29 is 12% of the free stream velocity. So we find a very slower evolution for 0.29 and a faster dynamics for 0.46. And what is the effect of this faster dynamical evolution of the bubble for 0.46? Well, basically, since we have a faster progression of the attachment point downstream of the bubble, we expect, and we also proved, that we have a higher rate of variation of the pressure per unit time, which corresponds basically to a higher lift rate. But it's now time to explain why we have so different flow dynamics between these two cases. We can explain this by analyzing the evolution of the flow field in a generic instant of time. For example, at t plus equal 1.45. If we analyze the distribution of the vorticity for these two cases, and I plot on this figure the corresponding position of the attachment point downstream of the bubble for these two cases, we see that in the case of 0.29, the reattachment point is closer to a larger scale negative vorticity concentration downstream of the trailing edge. And so what does it mean? It means that actually, since we have seen, but I have not shown here, but we have seen, and you can see it in the dissertation, that the shedding of this larger scale vorticity concentration associated with the shedding of the separated shear layer induces an adverse pressure gradient upstream. So since this point in the case of 029 is closer to this large scale negative vorticity concentration, it's expected that it feels a higher adverse pressure gradient than in the case of 046. And for this reason, it's expected to move slower than in the case of 046. So in this third case, in this third subsection, we have seen that we have compared three duration of the single pulse, in particular 029, 046, and 086. We have seen that 046 induces the maximum rate of lift variation because the bubble which is formed in this case has a faster dynamical evolution compared to the shorter case. While in the longer duration test here, the bubble is formed too late, and very close to the phase when the maximum lift is obtained. And for this reason, it has not beneficial effects on the lift increase. So actually, it's important, the optimal duration of the actuation is a compromise between the instant at which the bubble is formed and the corresponding flow evolution and distribution of the pressure on the airfoil at this phase. So I will. I hope that with this presentation and in this work, we have given useful insights into the understanding of the transient effects of the actuation. However, we can still perform some parametric investigation to find the parameters playing the major role in enhancing the rate of variation of the aerodynamic loads. For example, the time when the bubble is formed, or the pressure distribution, the pressure gradient at the point when the bubble is formed. And the master of these actuation parameters can be very useful to implement physics-based closed-loop control strategies that can improve the performance actuation of the actuation even beyond the current limitations. However, the control strategies that have been tested in this situation have been applied over well-defined quasi-steady flow configurations, as we have seen for the case of 14 degrees, when the separation appears from half chord. However, it will be very interesting to test if these control strategies are very effective in real unsteady flow configurations. For example, during pitching airfoil, so dynamic stall, or during gust, or during rapid maneuver. And so we can test if in this situation, these actuation laws that we test in this situation are able to alleviate the unsteady loads. But in every case, I hope that this work have given useful insight and have paved the way toward new application of a closed loop control in a steady situation that, for example, can be seen here. For example, we can think to apply our a steady control to alleviate dynamic stall over helicopter rotor, to alleviate the unsteady loads in the case of wind turbine blades, or even to control the maneuverability of aircraft. So, for example, in the case of a drone, or even to control the maneuverability of a dirigible. However, it's important to say that this is not the only technology that is able to control the unsteady loads of the airfoil. For this reason, we can try to test, to apply the fluidic actuation used in this work in cooperation with other technologies, as for example, you see here the smart morphing and sensing wind developed in the European project coordinated by Professor Brazza. So I want to thank you very much for your presence here, and I'm looking forward for your useful insights and the comments that will surely help to improve my work. Thank you very much.
Thank you very much, Armando, for this very clear presentation. We will start with the questions of the jury, and I would kindly invite Professor Ari Glaser, the first reviewer, for remarks and questions, please.
Wow. Okay. Well, first of all, I think it's a very nice piece of work, and I must say I recognize some of our earlier work in your overview, which was kind of nice. I mean, some of the figures actually look familiar. So I basically had several questions that I think you saw. I don't think we need to go over every one of them. Maybe we should just focus on the points that I think that might be a little bit more pertinent. So the first question that I have has to do with the fact that, and I noted it in the report that I sent, that unsteady pressure measurements are obviously very important for this work. And you noted that the frequency response of the scanner that you used was on the order of about 200 hertz, which basically gives you characteristic time, say, of about 5 milliseconds. And that corresponds in terms of dimensionless convective time to about 0.2 or something like that, or 0.24. Yes. And what I wanted to know is, have you looked at the effect of this response time? Because when you do your phase lock measurements, the time step between the measurements is essentially arbitrary, right? Because you can take data at whatever rate you want. Yes. And the same thing is true for the PIV that you're looking at. So the question is, did you make sure that when you are doing time increments that are very short, yep, okay, actually shorter than 0.2 in terms of convective time scale, that the pressure scanner can actually respond to that, or if it does respond, that the response is indeed accurate. Yep. Okay, so, and I only ask this because the time steps in these pressure measurements from which you derive the changes in lift, obviously, are very important to what you're doing in chapter 5. Of course, yes. Yes, thank you very much, Professor Grisa. Indeed, this is a very important question. And yeah, it's very important that I properly respond, because it's true that we have a limited frequency, acquisition frequency, which is about 200 Hertz. But these phase locked measurements were piloted. This means that actually it's has that control at which instant the acquisition of pressure that will appear. And so by doing this, I was able to perform phase locked measurements, for example, not only every 5 milliseconds, but every 1 millisecond. So in this case, we can imagine that the frequency of acquisition was even higher than 200 Hertz, but can reach up to 1 kilo. However, it's important to say that it's true that the acquisition at 200 Hertz will result in a limited bandwidth. So we cannot capture, for example, a steady phenomena for a frequency larger than 100 Hertz, for example. And this is true, but the phenomena that we capture actually have a frequency of about maximum 5 Hertz. And so we were pretty sure that our measurements with this acquisition system at 200 Hertz was giving the right result. And for this reason, in order to be sure, we compared the response of this pressure scanner at 200 Hertz with some unsteady pressure scanners that we placed over the cord of the airfoil, as you did in your work, because as you have seen from my presentation, it was a sort of inspiration for me, because when I started with my work. And so as you did, we compared this pressure scanner, the pressure from this pressure scanner with some unsteady measurements in just some points over the airfoil. And in particular, these unsteady measurements were doing at a frequency of 20 kilohertz. So very, very big. And we were able to compare the two measurements, and we were sure that the two measurements were giving exactly the same result. But to be more sure of this, we also performed some balance measurements
with an unsteady balance. And we also found the same evolution of the lift, of the pressure drag, and the pitching moment. So with this starting point, we have thought that the pressure measurements were enough to characterize the dynamical evolution of the flow field, even with these 200 Hz acquisition fragments.
Very good. Yeah, this is very convincing, and I would certainly recommend that you include these comments somewhere in the thesis. I mean, because I was actually looking for that.
Thank you.
So while we're on this subject, if you don't mind, I have another question. So when you did your PAV measurements, yes, you were able to, obviously phase locked, you have the vorticity distribution on both sides of the airfoil and in the wake. And in fact, for measurements like that, if you capture the full wake of the wing, you can actually measure the time rate of change of the circulation, and from that get an idea of the behavior of the unsteady lift on the airfoil.
Yes.
And I don't know if the PAV measurements were designed to give you the flux of vorticity through the entire wake, but I think that this is something that would be definitely worth looking at.
Yes, you are perfectly right. Indeed, we always, to compare with your work that you have carried out in the same domain. As I said, I took inspiration. So the first thing I did was exactly this. Indeed, with the measurements I took in the near wake, I calculated the vorticity flux through a line which is vertical, so a vertical line in the wind tunnel, and I did exactly the same thing as you did. So comparing this with the evolution of the lift. Although I have to say that I did not present this case for our configuration, because actually we were finding slightly different results, and sometimes even more than slightly different results, by moving the lines. And actually, I would like to ask you, sorry if it's really strongly related to the position of the line, the computation of vorticity, because.
So,
yes, because I've seen, for example, in your work, you have placed the line at about one chord downstream of the trailing edge, if I'm not wrong, 1.25, something like that. So actually, is it really important, the position of the line in the calculation of the vorticity flux? Sorry to ask.
Oh, no, not at all. So first of all, this is a very good question, and because you can imagine it came up before. In principle, if the flow is two-dimensional and you're dealing with a two-dimensional model, a carefully designed two-dimensional model, so that you don't have to deal with tip vorticity and all that kind of stuff, the flux in the wake should be pretty much independent of where you're doing the measurement, because all the vorticity comes from the airfoil.
Yes.
What limits, at least from our experience, these measurements is the fact that if you're too close, your resolution is not insufficient, and if you're too far away, the vorticity's flux becomes, or the flux becomes distributed, the magnitude of the vorticity goes down, and then it's makes it a lot harder. Again, you're getting into resolution of the PIV. So there is a balance between the two. But in principle, this really shouldn't matter if the measurements are correct. I would certainly be interested to see,
yes,
and this is the reason I brought it up, is that to see if the time-dependent lift that you have from the pressure measurements agrees,
yes,
at least, never mind so much in magnitude, but at least in the features and the derivative, okay, the time dependence compared to what you got from the pressure. That's
indeed, yes, you are perfectly right, and indeed, thank you very, very much for your advice. I will try again, and I will because I will try again to measure the vorticity flux. However, I'm sure that the behavior of the lift calculated using the vorticity flux in the near wakes was the same of the one measured using unsteady pressures. So this was sure. The problem for me was the magnitude. We did not have the same magnitude depending on the position of the line. And for this reason, I didn't put this in my dissertation, but because I think it's really yes, because in the case of for example the Kelvin-Helmholtz theorem, it's potential flow, so we are also neglecting the dissipation. However, if we take a line, for example, 3 chords far away from the trailing edge, we are expecting also the amount that there is a big dissipation in the wake, and so the measurements of the vorticity maybe cannot be related enough to the variation of the lift. Maybe I'm wrong, but this is why I expected also this slightly change. But I will show you as soon as possible. I will show you the variation of the circulation calculated with the vorticity flux. Thank you very much for this question.
Sure.
Because yes, it's very important. Thank you.
So I don't know. How do you want to do with it? I have just basically 2 more questions. So if maybe I can ask them now and we'll be done. So the first question has to do with the identification of the essentially the intersection of the reach from the Lagrangian approach with the surface of the airfoil, and as the boundary that defines the separated flow region. I looked at the streamlines that you computed, and in fact, you can actually compute particle trajectories just as easily from the phase average data. And it seems to me that, why wouldn't you use the saddle point, for example, that is formed by a streamline compared to the Lagrangian approach that gives you this red line that intersects the airfoil that is not exactly clear what it means physically.
Yes.
For that, they may very well give you the same results. It's just that it wasn't clear to me why one is better or more meaningful than the other.
Yes, thank you very much. In fact, this is a very important point of my work. So I'm glad that you are asking this. In fact, yes, the problem with streamlines is that they can gives an idea of what is the flow evolution of the airfoil. Of course, even in unsteady situation, that's indeed all my measurements of vorticity. I always superimpose the vorticity and streamlines, and we were able to get the evolution to get the evolution of the flow field even by looking at streamlines. The problem was that since the streamlines in the unsteady situation are always tangent to the velocity vector in every point, in our unsteady situation, actually the particle trajectories that are calculated are, of course, of course you know, but it's they are completely different from the evolution of the particle trajectories. So for this reason, if we are tracking the instantaneous position of this saddle point, we cannot use streamlines to track the exact position of this point. Of course, streamlines gives an indication of how this point is moving, but they provide misleading information on the real transport behavior. And for this reason, we had to use another approach with this Lagrangian approach. And in fact, if you can see in another way this FTLE, this red line, actually this red line divides topologically different flow behaviors. So if I can come back with my presentation and we see, for example, the red line, I just go with a picture of the red line I showed before. Just 1 second, please. Sorry. Yes, for example, it was here. For example, you can see here that actually this line, this red line, this ridge here, actually separates two different regions of the flow field that have a very different topological behavior. And indeed, one of the most important property of this red line is that there is no mass flow rate between this line. And so actually, you can see that, for example, if you calculate the instantaneous separation over the airfoil, you want to, for example, to divide the dead air zone in the separated region and the flow with a certain velocity. and you can do it by analyzing this FTLE value. And so this FTLE will give you exactly the difference between these two regions. And so it's an indicator of the real topological behavior, or in other words, I can say of real flow transport over the airfoil. And for this reason, it's more accurate to predict the instantaneous position of the attachment points compared to the streamlines. And so for this reason, we preferred to use the reattachment point to detect the position of the attachment point, to use this FTLE. So I don't know if I was quite clear or not. You can.
Well, the only point that I would make is, I mean, as long as you define
Yes.
the characteristics of, you choose the topology, it really probably doesn't even matter. The only argument that I would make is that even though the flow is unsteady, clearly unsteady, you have the instantaneous phase log, instantaneous images of the flow, and from that it's almost trivial. I mean, you've done this to calculate the streamlines. Now, obviously, these are unsteady streamlines, and you cannot argue that there's no mass flux across the streamline, but I don't think that that's really the important point here, because you do have a settle point that is on the surface. In fact, this figure that I'm looking at actually shows it a little bit upstream of the where the red line intersects the surface. So,
Yes.
I think that they might have, probably will have the same dynamics.
Yes,
Okay.
if I can say another argument that I can say I was thinking about during your question, indeed, is the thing that actually I'm able, for example, to calculate another streamline very close to the streamlines, the streamlines here that presents the hypothetical reattachment point. If I calculate it, for example, in a point close but not sufficiently close, I can find another intersection with the airfoil. And actually, this means that actually is not is ambiguous, the position of this point, if we calculate it, for example, by using streamline, because it depends on which point you are seeding the streamlines, and so you will find a different position of this point. And so actually,
yeah, that I think would be probably a deficiency of the data and the resolution of the PAV near the surface. Because if you know the velocity field, then, and the flow is circulating within the separation region, then the flow should be turning around.
Yes.
It is true that when you do PAV close to a surface, you have reflections, you don't resolve the flow all the way to the surface and so on. So defining these points may take a little bit of fine tuning of the integration algorithm, because you are integrating forward to determine the critical points. But other people have looked at that. Again, no big deal. It's just something that you might want to look at how people work with definition of critical points. And it's true, when you're dealing with PIV, you may not have the resolution that would be sufficient to look for these points near the surface.
Yes.
Okay. The last thing I want to ask, which is my last question, one of the very last plots that you show in the thesis compares the transient actuation when you do periodic actuation, right? So you do transient actuation, and then you do time periodic actuation, right?
Yes.
Or pulse actuation and time periodic actuation. And the difference between, you have 3 plots there, and this is all from memory.
Yes.
But the transient actuation that was nominally smooth, in other words, you didn't get the oscillations, and the time periodic actuation had slightly different CMU, okay, however which way you defined it. But the time periodic actuation yielded higher lift,
yes,
and the same drag,
yes,
okay, as the pulse actuation.
Yes.
So, obviously I'm biased towards pulse actuation, but you look at this result, and if I'm Airbus or Boeing or whoever, okay, in that order probably, because you guys are in France, I'm asking myself, why should I bother? Here, I think it's this plot, right?
Of course.
I'm asking myself, why should I bother? Okay, I mean, I can get, slightly better results with the time periodic actuation. Yes, the CMU is a little bit higher, but the drag is the same. Actually, there's higher CMU, I'm getting more lift.
Yes.
Okay.
Right. Of course.
There's less hardware. I don't need to worry about, this pod stuff and so on. Why should I even bother with that?
Yes. You're completely right. Indeed, it's not very easy to sell this product in this situation. Indeed.
Now you know why I have a lot of white hair.
No, I want just to reply. For this reason, I carefully read your comments, and so I prepared a slide to try to explain why Boeing should buy my product.
I should buy it first, but it's okay.
I'm sorry. No, anyway, you are completely right. Indeed, we find that steady actuation with CMU that is almost 4 times than in the case of the periodic actuation induces a very higher lift, but drag which is comparable with the case of the actuation, periodic actuation. So they say, look, but we obtain a lift which is 30%. The other one is 20%. So we are increasing 10% more the lift with not so much CMU. So steady actuation should be better. However, for this reason, I did another plot. And here, actually, I take into account also the power consumption of the flow of the actuation system. Indeed, this FM that I've looked in many papers, it's called the figure of merit, and it's actually the ratio between the lift produced by the actuation and the pressure drag plus the jet momentum coefficient, which gives an indication of the consumption of the actuation system, divided by the baseline efficiency of the airfoil, or the baseline lift-to-drag ratio. So basically, if this figure of merit is higher than 1, this means that the actuation is given a beneficial effect compared to the baseline configuration, because we are taking into account also the energy expenditure. So if this figure of merit will be higher than 1, we are sure that the actuation is beneficial. If this figure of merit is lower than 1, Boeing will never buy our product. Or in France, we can say Airbus. In any case, if we compare these 3 actuation laws, we see that actually the periodic actuation that exploits the transient effects between the repetition of the actuation actually produces figure of merit which is slightly higher than 1. So this is beneficial for the performance of the airfoil. But in the case of the steady blowing, since the CMU is 4 times higher, we produce a figure of merit which is lower than 1. So actually, we are able to gain with the periodic actuation if we take into account also the energy consumption of the system. And so this is the reason why. However, I have to tell you, I'm honest in this case. I have to tell you that actually we didn't, I'd say, put much focus on this. Actually, this was, let's say, the last part of the work. I really tried a lot. I took one experimental campaign to try to find some actuation strategies based on my previous physical knowledge of the flow field to increase a lot the performance compared to the steady actuation. Actually, I'm honest, it's not very easy. I mean, if you don't use closed loop strategies, it's very, very hard. And so for this reason, I try to see things in another manner. I see, okay, but if we consider also the performance, the energy expenditure of the actuation, what we'll get? So for this reason, I compared the two response, and actually we can see that actually the figure of merit is higher than 1 in the case of the periodic actuation. So I say I can just say I cannot prove it's the good way of actuation, but I just say that we can maybe focus more on the exploiting of the transient effects of the actuation instead of sending a huge amount of power using steady blowing.
So I'll finish with that, but the one comment that you may want to check if you want to feel better about selling this to anybody. One measure that is missing here
Yes.
Is the fact that you know how much power you need to expand in order to push the jet through the orifice, right? Because you know the mass flow rate.
Yes,
I assume you measure that. And you know the pressure change or the pressure drop across the system that drives the jet. So there is power that is associated, or the fluid power that is associated with the two methods of actuation. And I think that if you look at the actual power that you dissipate, the cost to run the actuation, considering the mass flow rate and the pressure drop that is generated, that you may be far ahead with the pulse actuation as you are compared to continuous actuation. CMU does not necessarily measure what happens here, because the question is how much or what does this CMU cost you?
Yes, yes.
And that is not in this plot.
Yes.
Anyway, I'm done.
You're completely right. Thank you. I will.
Thank you.
Anyway, if it's possible, I will try to maybe send you, I don't know, the computation with the CMU multiplied by the velocity. Like that, I will have the power. Jack is saying me that from months, maybe. He's saying me, but no, look, we have to put the power. And I'm sorry, I never changed. Sorry, Jack. Thank you very much.
You really need to look also at the pressure drop across the system. Okay. And that because if you take power, say, from the engine, or you have a compressor or something that drives this is the cost. It's the mass flow rate, m dot times delta p.
Yes.
Okay, and that's fluid power. That's it.
Yes, I also noticed that.
Okay, thank you very much, Professor Glaser.
Thank you.
Now, may I kindly request Nicolas Mazelier, reviewer, also to ask questions and remarks. Please, Nicolas.
Thank you, Mariana. Can you hear me, Armando?
Yes, I can. Thank you.
Okay, perfect. Thank you very much for this presentation and also for the manuscript. I really enjoyed both. It was quite interesting to see it, and I have also plenty of questions. And I see that you feel much better compared to the presentation in the conference in Rania, so that's also very nice.
Yes, that's always good.
I have some questions also related to questions by Professor Glaser. And first of all, I want to know if you have some ideas about the potential 3D effects you have in this flow, because the model is 2D, okay, but the control is 3D, and this might have some effect, I guess.
Yes, of course. This is you are completely right, Professor Mazelier. Indeed, yes, the baseline flow is 2D, but actually when we apply the actuation, it turns out that we have a very strong streamwise vortices that are generated by these jets, and actually, yes, the flow field in the general sense is 3D. However, if I may respond to you, I prepared actually another slide. I just maybe can plot it, because actually we expected that the effects are 3D, but we were, how to say, sure that what we measure for example, in the mid chord will not be strongly different from what we measure for example, in another location. Of course, maybe very slight difference. For this reason, in the first exploratory campaign we carried out back on 2017, when I was doing my master internship at Institute P', we actually measured the variation of the loads also with the balance. Okay, now these plots here, you can see here, actually compare the evolution of the lift, pressure drag, and pitching moment obtained with the balance and with the unsteady pressure of the airfoil. Yes, of course, here we should filter these results. These results were, I just took the images we did at first, so sorry if it's not really filtered. We just removed the characteristic frequency of the structure in order to be sure that to not perturbate our results with the characteristic frequency of the structure. But we decided not to remove all the other frequencies in this response of the balance because they can be associated with aerodynamic loads. So it was the first campaign. So with this in mind, we can now compare actually the evolution of the lift, for example, which is the most important indicator. And actually, we see that actually the response to the pressure, the black one, measured at at mid-span, with the response of the balance is very, very close, even if the balance take into account all the 3D effects of the actuation. And so by looking at these graphics, we were pretty sure that our measurements were not, let's say, wrong, and that if we take another exploratory plane slice in another part of the airfoil, we will not obtain something which is really different. However, I agree with you. To be precise, we should maybe take more than one slice over the airfoil span, and maybe average the measurements in this slice to get a better indication of the variation of the lift over the wing. However, we didn't do this, so I'm sorry, but we are pretty sure that our responses are not so different from what we expect from considering the 3D effects.
So just to give you an example, we are using now in Orléans a swept airfoil.
Yes.
And obviously there is a 3D effect by the geometry, but we don't see so much difference also from balance and pressure measurements on the mid-span, because as far as you are not fully detached, so before stall, in fact, this is not very strong effect. But we see clearly by using some Tuft visualization and things like this, for example, that there is a 3D flow along the spanwise direction.
Yes.
So maybe why did not use the PIV measurements? Because in the PIV measurements, you may have some ideas about the importance of these 3D effects.
Yes. Okay. To be honest, the first problem for the PIV is that, for example, we could have used the PIV plane, for example, which is normal to the plane that we use now. And in this case, we could get, for example, if there how much.
No, even with the plane that you have used in the PhD.
Yes.
If you look to the divergence, the local divergence.
Yes.
You will have an idea about the effect in the third direction.
Yes. This is very, very, very good advice. Yes, indeed. Yes, I didn't think about that. I just thought about taking other planes to check if there were strong 3D effects. Yes.
Because it may have some effect about what you said before about the computation of the flux of vorticity, which was, it seems, dependent on the position where you were using the PIV measurements.
Yes, yes. I will check. I didn't check. I'm honest. I didn't check this. But I will. I'm noticing it, and I'm noting it, and I will check as soon as possible. I maybe send you a message to inform you if there will be we can detect 3D effects from the PIV. Yes, but actually I didn't check because I was expecting that the pressure in the mid span were almost well representative.
Yeah, I understand.
I'm sorry.
No worries. Another question is about the method you use to track the reattachment point for this recirculation induced by the control by the pulsation.
Yes.
And I was very curious about this method because I've never used it before, and it was very interesting to see it. But I have some question about this. For example, you said that you have a slip condition that you use close to the wall.
Yes.
So it is like if the method is using a potential flow.
Just
correct or not?
Yes.
Is it coming from the method itself, or because you have no way of making something else?
No, actually, your first say because actually near the surface of the flow, as you can as you know, actually we had although we used a very special paint for PIV, and with all the care that we took to ensure that there were very few laser reflection, the flow in a region of height 5 millimeters next to the surface was strongly affected by the reflection of the laser. And so actually we could not accurately analyze the flow field in this region using PIV.
Mm-hmm.
It was too much inaccurate. The uncertainty was very big, and I was not sure that the vector in this region were right, even though we take all the care to make. And for this reason, we prefer to replace this 5 millimeter height region with a potential flow field that was calculated basically using slip boundary condition. And so with this method, actually, I test even another kind of I'd say of measurement. I try to put the velocity on the wall equal to 0 to test if there was any difference, and I also try to test without this boundary condition, and actually we did not have a very strong difference on the position of the red line, because actually the scales of this region that is resolved by using slip boundary condition are very small compared to the transport scales of the phenomenon. And so actually we don't have any problem to detect the red line even if we make a small assumption near the wall. So for this reason we used slip boundary. It was okay, it worked, and we went on with this, and we had no problem compared to other methods or without it. So that's why.
Okay. It could have been good to compare it with, as for example, Professor Glaser said, the saddle point position and the velocity of this convection term, for example. And also, can you compare it, this X attachment here? Can you compare it to some zero crossing of the pressure distribution, evolutions, things like this? Because at the end, if you are thinking in terms of airfoil application,
yes,
you may have some sensors on the airfoil and not this method. And can we use it at some point to make some feedback control and things like this?
Yes, I think so. Of course, I think that we can. However, I would like to, if I was, it was me to perform some closed loop control strategy, I would like to use a film to detect the skin friction coefficient, and the point where the skin friction goes to 0. It gives you an idea of the reattachment point. Of course, it's not precise, but at least with an error of 5% of the chord, we can give an indication of the attachment point. And so, yes, I agree with you. In a real case, we cannot use this method, but actually, this method helped just to understand the dynamical evolution.
Yeah, I understand.
We didn't want to perform it in a real situation. So yes, you're completely right. Of course, in a real situation, it would be better another kind of approach.
But I think maybe you have everything to compare it.
Yes, of course. Yes, this is yes, indeed, yes. The first thing is, as you are saying, and Professor Glaser said also before, the first thing is to compare the velocity of movement of this point with the velocity of advection of the point detected through streamlines. So if these velocity are quite similar, we can already say something. And yes, of course, we can also use we didn't perform skin friction measurements, so I'm sorry we cannot go in this direction. And with PIV next to the wall is not well resolved, so even in this with this method it was not so easy. Actually, with our measurements to detect the position of these points, we have two opportunities: or we use streamlines, or we use this Lagrangian approach.
And you don't think that the pressure measurements can be used?
Yes, of course, but actually there was a work that was developed, I remember now, by a paper of Christoph about the root mean square of the pressure variation over the airfoil. And actually, if I'm not wrong, probably Christoph will correct me because it's years I've read it, but it was correlated with the maximum root mean square of the pressure variation. So there is a correlation between the position of this point and the root mean square of the pressure variation, the maximum root mean square of the pressure variation over the airfoil. And maybe it's really it could be really nice actually to compare the position of this point you obtained with the streamlines with FTLE and by using the pressure distribution over the airfoil. So yes, I will note that, and I will try to do to do it as soon, because now it's very interesting. If it's really the same position of, for example, FTLE, we can prove that we can, I would say, not prove, but let's say strengthen our hypothesis at least.
Mm-hmm. And here you are focusing on, I will call it an advancing point, because it looks very much like a spreading of the liquid film, going around the surface. Did you look at the upper part? Because finally, from your manuscript, I understood that the pressure, the region where the pressure is favorable for lift increase,
yes,
is not only downstream the actuation, but also upstream the actuation.
Yes.
Correct or not?
Yes.
So I guess you've got something, a sort of bubble which is also going upstream.
No, actually, yes, you're perfectly right. I will try to show this by presenting the case of an unsteady flow field, because unsteady case. So, for example, let's consider this case at 16 degrees, and I explain you why I show you, because actually, yes, as you said, there is an effect also near the leading edge of the airfoil. However, for example, if you take into account this configuration, we see that the flow is fully attached. But if we take the pressure variation in this case, we see that actually there is a very strong suction near the leading edge, and this is the same effect of what we registered in the steady case. So even if there is no bubble downstream, we have a strong suction near the leading edge. So actually, this suction is not related to the presence of the bubble, but is related to the fact that by creating the bubble and modifying the flow in the near wake, we are changing and this is something that I've read a lot in the papers of Professor Gleiser. We are changing the aerodynamic, instantaneous aerodynamic shape of the airfoil. It's like, in other words, we are increasing the camber. By increasing the camber, we are moving the stagnation point toward the trailing edge. And so this corresponds to have an airfoil with a higher camber, and so it will result in a higher suction near the leading edge, even if there is no bubble at all. So it's just an aerodynamic shape of the airfoil that induces this change. So it's not related to the bubble, this suction. If I
so this bubble is attaching, and this attachment is going downstream toward the trailing edge.
Yes.
Is there any receding angle close to the actuators, or is this bubble fixed in space?
No. Yes. No. Actually, no. If we can see maybe from this video, yes. No. Actually, the bubble. Maybe you can see from this video. Actually, if you see here from streamlines, that gives at least an indication of the flow. actually you see that this bubble, this reattachment point is not only moving toward the trailing edge, but also the bubble moves toward the trailing edge. And
so there is a closed part
yes,
which is also moving.
Yes. And indeed, just upstream of this bubble, the flow becomes reattached. And so, and so what we obtain is what I showed in the figure just here. Actually, what we obtain is that we have a closed bubble with the flow just attached upstream, and a shedding of vorticity in the near wake. And actually, if we compare these schematics that I have shown here with the baseline case, is like we are operating with an airfoil with a higher camber, and the stagnation point moves toward the trailing edge. So we have a suction in this zone because we have a reattachment flow, and also because we changed the camber. However, this suction will also continue below the bubble, because since we have a separation bubble, the pressure is fixed at the point of the separation. And so actually we have an unsteady pressure that will develop also below, a negative pressure that will develop also below the bubble. And so actually when the bubble moves downstream, we have suction here because the flow is reattachment, suction downstream, below the bubble. And so we extend the suction all over the surface. For example, I show here, I prepared another slide to show this. Maybe you can see here, for example, here, from this slide, we see that at T+2, the bubble has almost reached the trailing edge. And actually, if we compare the pressure evolution for the lift, we see that actually the negative variation of the pressure has reached the trailing edge almost. And indeed, before the bubble, the flow is attached, so the pressure is decreasing because there is suction. And downstream of below the bubble, the pressure stays at almost the same value at the separation point. So we have a depression even below the bubble, which reaches almost the trailing edge. And so yes, you're right. It's also the dynamical evolution of the flow field upstream, but is not directly related to the presence of the bubble, because this depression here, it will appear even in the case when the actuation is steady, so we have no bubble at all. The only difference, you can see here, because you compare the red and the black one, and you see there is almost the same suction upstream of the bubble. The only difference is just below the bubble.
So this bubble is quite interesting in terms of lift.
Yes.
And would you think that because here you're making just a single pulse blowing?
Yes.
Would you think to a strategy where you will be able to keep this bubble attached on the airfoil? Do you think it's possible?
To keep it attached or to keep it always in place?
In place, let's say.
Okay. Yes. I think it's
so that the situation that we have here on the figure on the top is let's say steady.
No, here is when is after the single pulse.
Yeah, I understand. I mean,
I'm sorry for
this recirculation stays here for long.
Yes, I agree. Okay. Yes, we tried to exploit the presence of this bubble. I made, for example, some periodic actuation by changing, for example, duty cycle, the duration of the pulse. So it's just some single pulse that are repeated in time and all this. And actually, we tried to take this bubble in place as much as possible. And this is what I showed at the end when I just showed before to Professor Gieser. We obtained this periodic actuation here. I show you the lift, for example. For example, in the red case, the time distance between the time delay between the two actuation pulses are enough to provide the generation of the bubble between two consequent pulses. And actually that's why we have this this oscillation actually. And because we are able to generate a bubble between the two pulses. However, for a case of the higher frequency, so the blue case, the actuation was too big, too high. The frequency of actuation was too high to keep the bubble in place between two different pulses. And so,
yeah, but do you think? Yeah, because here you are using the same type of actuation, which is pulsed jet.
yes.
Do you think if you use something else like a synthetic jet,
Mm.
where you can play with an asymmetry between the blowing and the suction phase?
You are completely right. You are completely right, because actually this is again, sorry to cite always, but is I read on the always on the work of Professor Gleiser, because they actually worked on the effectual on the virtual aerodynamic shape of synthetic jets. Actually, if you are operate synthetic jets with a frequency which is a order of magnitude higher than the frequency of the global instability over the airfoil. So, for example, if the shedding frequency is 2L02, you use 2L2, or if just to say, and actually they were able to create a separation bubble over the airfoil that was in place for all the time where actuation was performed. However, this is another case where actually they exploited the aero shaping effect of this bubble to increase the lift, if I'm not wrong, in a time average sense. So actually they were increasing the camber of the airfoil and consequently increasing the lift. However, we were doing something different. We were actually trying to exploit the formation of this bubble. Because if we create this bubble and we take it in place for, I don't know, for forever, so we don't move this bubble, we increase the lift, but in a steady sense. Indeed, what we wanted to do is to increase the rate of variation of the lift. And you can do it just by generating every time this bubble. And so there is a slight difference, because we are trying to exploit the transient effect of the bubble, while if you take it in place forever, you are only improving the camber of the airfoil, and so increasing the lift in a time average sense. But you don't care about the transient phenomena related to the formation of this bubble. I don't know
Okay.
if I was if I answered.
I have still two questions, but I don't want to be too long. Mariana, can I take them?
Yes, please go ahead.
So the first one is very surprising for me, because maybe I missed something. If we go to page 84 of your manuscript,
Yes.
it's the figure 5.1.
I just one second, sorry, Professor. Please.
Yeah, sure.
Can you please repeat me the page and the figure number?
84, figure 5.1.
Okay. Yes. Okay.
And I was looking to the black curves, which was there is a transient effect of a steady blowing.
Yes.
So I was expecting that the final state of this blowing should be comparable to the figure 4.14, for example, which was on the chapter about time average.
Yeah. Okay, understood. Yes.
So I was quite surprised that I don't find any level
You're right.
for the angle of attack. So did I miss something?
You are completely right. Yes, indeed. I don't remember if I wrote it, but in a very short phrase, maybe, or I didn't write it at all. I don't remember. I will check. Anyway, you cannot compare the both figures, because in the case of the figure 5.1, you have that the steady blowing is performed with a maximum jet exit velocity of 100 meters per second, which is 5 times the free stream velocity. While in the case of figure 4, in the chapter 4, the steady blowing was not performed with the same jet exit velocity. But
the CMU is the same.
Can you say me which figure?
4.14.
Okay.
Page 78.
Okay.
And the difference is huge.
Yes. Yes, actually there is a small, yes, I agree with you about this. Actually there is a small difference, and I was expecting that someone was noticing it. Indeed, is important to clarify this point, because actually if you the steady blowing that we are performing in chapter 5 is not really a steady blowing in the common sense, because actually if I go in figure 5.1, we see that the steady blowing is nothing but the phase locked the measurements, because we had to phase average the variation of and so we could not take, for example, steady blowing for 10 seconds, then stop it, and then because it will take 1 month only to make few measurements. So for this reason, we stopped it a little before. And so the steady blowing can be referred as for example, was taking on for example, 2 seconds or 1 second, and then took off. And so, yes, this can lead to slightly different results in the maximum lift that was obtained. Why?
Okay.
Because actually, when you take on, you switch on the steady blowing and then you switch off again, if you don't wait a lot of time, maybe 5 seconds, something like that, to give you an idea, it will not come back to the exactly the same baseline configuration of before. It will be time average, in a time average sense, it will be the same, but the pressure will not come exactly to the same position as, and that's why you find that slightly some differences between the time averaged measurements and the transient measurements, because actually if you want to perform it in a very let's say to have the same results, you should actuate the jets with steady blowing for 10 seconds and then wait 10 seconds for the loads come back to the state when they were before.
Okay.
It will take an incredibly huge amount of time, and so we did not do the transient measurement in this way. However, to be sure that we were obtaining the same results, I compared the derivative of the steady blowing obtained in this chapter 5 with the case when the steady blowing is performed in the proper sense of steady blowing. So took on switch on steady blowing 10 seconds, switch off steady blowing 10 seconds, and analyzing the derivative of these two evolution of the loads, and it was exactly the same. So we were not changing the derivative by doing that, but just as a bit the maximum value that
the maximum. Okay.
So it will not have some issues on the analysis of the loads of the steady phenomenon. That's why we did not do this.
Okay, and my last question is about the you tried at the end of chapter 5 to take a specific point which was on the close to the trailing edge on the pressure side.
Yes.
And this is interesting because if you think still in terms of application, then you need a sensor to make some feedback control.
Yes.
And this was quite interesting. However,
yes,
I'm not very clear about why this point is so interesting in the sense, if you look figure 5.9, where you compare the evolution of the pressure and you see this point, which is close to C equal 1. You don't see so much difference between pressure side and section sides.
Yes.
So this point has no effect on the lift, I would say.
Yes.
Compared to others, which are much more sensitive to the effect of a pulsation. So can you clarify this point?
Yes. Yes. Okay. I was expecting this question. Of course, because I read your report. Of course, you are right. If you look at the figure 5.9 in the manuscript, or even the other one when I compare the different duration of the single pulse, from this figure appears that we don't have much difference from the pressure variation between single pulse and steady blowing. However, if we analyze, I will show it in two cases. We can analyze, for example, the pressure variation for the case of the steady blowing and single pulse, for example, from this video, which is exactly the same video as before. I will also plot on the you will see, I will plot the evolution of the pressure. Sorry, this is only on the suction surface. I will take the one I did on the, okay, this one. Yes, if you look at the evolution of the pressure, this is, in this video, we have the same graph as I showed in the manuscript. So we have the variation of the pressure both on the suction surface, just to clarify. And actually, if we look at this picture, this video, and we follow the evolution of the pressure, sorry, I want to stop the video at. I want to stop the video to take a snapshot. No, I'm not able. For example, let's look, for example, here. You see that actually there are, although there are few differences, but there are some differences. The pressure distribution near the trailing edge induced by the single pulse in red and the steady blowing in black. And actually is not just 1 point, but there are, I will say, up to 0.8. We have a different distribution of the pressure between single pulse and steady blowing. And actually, I tried at last to try to explain this global effect. I tried to take some points near the trailing edge, and I said, okay, let's look what will happen if I analyze the lift in this. And actually, I found that the evolution of the lift in this point was very close to the global lift evolution. And it was quite interesting because actually, if we would like to develop some closed loop control strategies, for example, based on for example, on the physics of the phenomenon, we could measure the pressure just in some points, for example, near the trailing edge, and we will see what's happening on the global lift evolution around the airfoil. So it's like a sort of indicator, let's say. And this is very interesting. However, I agree also with you that we must look at the integrated effect of the pressure all over the pressure surface. And for this reason, you can also look to these graphics. Here, you see, for example, the same points, but I also plotted for other let's say other duration of the pulse.
Yes, okay.
See that, as before, we have different evolution, and in the case of delta T plus 0.5, we have the maximum rate of the pressure. And it's because also for the lift, for delta T plus 0.5, we have the maximum rate. And if we analyze now the integrated effect of all the pressure on the pressure surface and on the suction surface, so on the left is suction and the right is pressure surface, we see that is not prominent, but we still have this rate enhancement by considering all the integrated effect of all the pressure on the pressure surface.
Okay.
So I think the phenomenon is really global. It involves even the pressure surface, and it's very clear by analyzing this distribution of the streamlines, because as I said before, it's like we are changing the instantaneous shape of the airfoil, and so it will induce a global dynamical evolution of the flow field.
Okay, thank you.
Thank you very much.
Thank you very much. That was my last question, and congratulations for the nice work you've done.
Thank you, Professor Mazelier. Thank you very much.
Thank you very much, Nicolas. Now, I would kindly request Guillaume Martinat, doctor engineer at the company Flying Whales, to ask questions, please.
Thank you, Mariana. So thank you for inviting me to this jury first, and I enjoyed reading the manuscript. I had a few questions that were answered in the presentation, so I also enjoyed the presentation. Thank you for that. I still have a few questions, however.
Thank you.
So I think it's page 69 where you're of the manuscript in figure 4.7. You're showing so the efficiency actually of the controller, and this is one of the questions I had is that you're solely using the pressure contribution to drag in order to evaluate the efficiency of the profile, but you're also stating somewhere in the manuscript that the jet, I mean the actuator, is increasing viscous contribution to drag. Did you have means to evaluate how this can modify the real efficiency of the control?
Okay, yes. To answer your question, yes, I prepared a slide because I expected this question because it's the okay. If you look at this slide, actually you see that this is the prediction of the ratio between the pressure drag and the total drag of X-foil in red, and in green there is the measurements performed by the work of Pak in 2008. And in particular, they measure the total drag using a balance, and the pressure drag is using the pressure taps. And so they actually, I made the ratio from their measurements. I made the ratio between the pressure drag and the total drag. So okay, so if we now look at incidences below, for example, let's say 8 degrees, we have the ratio between the pressure drag and the total drag is below 50%. So it means that the skin friction drag has a really big impact on the drag, on the total drag. So for this configuration, you are completely right. And indeed, if we perform actuation in this configuration, we will not only modify a bit the pressure drag, but we will surely increase the skin friction drag, because we are putting momentum in the boundary layer, and so this increases the skin friction drag. And so we will expect that the drag will increase even higher than what we measured. However, for high incidences, for example, let's say for incidences above 12 degrees, we see that, and especially for incidences above 14 degrees, we see that the total contribution to the pressure is given by the pressure drag. Because of course the total contribution to the drag is given to by the pressure drag, because we have a big separated region. And so for this reason, at these incidences, when we experience an increase of efficiency, is a real increase of efficiency, even if we take into account the skin friction drag, because the contribution to the skin friction drag to the total drag is very small, is less than 10%. And so even if we increase a bit the skin friction drag, it doesn't have a big effect on the total drag reduction that we obtain, for example, at 16 degrees. I don't know if I answered to the question, but I hope it's because there is a bifurcation between low incidence and high incidence. At low incidence,
basically what you're saying is that at least for higher incidence, the skin friction drag increase that you have due to the control is not significant.
Yes, that's what I mean. So yes, of course, for low incidence, our results are not reliable, let's say, because we may just measure the increase or the modification of the pressure drag. But if we take into account the skin friction drag, we'll have even a higher increase of the drag, because it's well known that the actuation will increase the skin friction drag over the airfoil. And so yes, for low incidences, it's not reliable. However, for high incidences, yes, I think our measurements can give an idea of what is the total drag variation.
Okay.
Thank you very much for the question. Yeah, it was important to clarify this point. Thank you very much.
You're welcome. So I had another question. I have several other questions, sorry, but one other question is on slide 40. I think it's 42 of your presentation, when you're showing different actuation period.
Yes.
For the same simu, which, if I understand correctly, is mass flow rate of your control.
Wait, slide 42.
I think it's 40 seconds, yes.
Isn't that? 2 is a transient effect. Is this one?
Okay, so maybe I did not get the slide. But so at some point when you're looking into, yes, no, it's not 42. It's definitely not 42. It's
okay,
way in the end.
Like this one?
When you're looking into the effect of the period of your control, yes, of the jet.
Yes.
And showing that, I believe it's for I don't have the period in mind, but basically when you have a shorter period, it doesn't work as well as when it's a bit longer, and if it's even longer, you're getting back to something close to continuous control.
Yes, is exactly.
So I had a question on that, because if you have constant simu, yes, exactly, it's on this one. Okay. So 0.46 for what you're looking at is basically an optimal. On what you're looking at. However, I believe that if you have constant simu, you have the same mass flow rate as a function of time. So you're putting more energy into the flow in the case of 0.46. So have you tried to check, and if I understand correctly, when you have a period of 0.86, basically what's happening is that the acceleration and deceleration of the jet are too decorrelated, and you're not getting the transient effect that is leading to the spike in lift. Have you checked something at constant energy of control? Meaning that if you're extending the period, then you have to decrease the intensity of the jet, and comparing all that, because then you're at constant cost.
Yes, you're completely right to ask this question, and I think it's important to also clarify this point. Yes, unfortunately, I didn't check to change the duration of the pulse by taking the same amount of mass flow rate, for example, because we had to fix a parameter that was, let's say, the same for every duration, and we fixed the maximum velocity. So we said, okay, we will do we will perform all the duration of the single pulse with the same maximum velocity, which is fixed at 5 times the free stream velocity. But however, we didn't check, and it's a bit also complicated, because it will take a longer time, because to fix the maximum velocity, you just measure what is the supply pressure needed to attain this velocity. However, if you want to change the duration of the pulse, you have to take every time hot wire measurements to see what is the velocity if you also change the intensity of the actuation. And so it will take a really long time, because every time we test not only these 3 duration, but I test many other. And actually, if every time I had to check the exit velocity of the jet, it would have taken an enormous amount of time. So we said, okay, let's fix the maximum velocity as a parameter, and let's operate all the single pulse duration with the same maximum velocity, which seems reasonable. But we didn't check also the so I cannot give you an answer. But I think, it's my opinion, by working with this, actually I think that maybe the duration of the actuation for which the maximum rate is attained will change a bit if we take the same mass flow rate for these 3 cases. However, I think the dynamical evolution of the flow field will not change, because actually, even if I perform at 0.86 with the lower mass flow rate to have the same momentum, the same consumption of this shorter actuation duration, I will in every case reattach the flow field for a longer time compared to 0.29, 0.46. So even if I perform it with, let's say, the half of the mass flow rate, I'm sure that I will reattach it, because we test it also with the lower mass flow rate. And so the derivative of the lift will be also lower. Yes, I agree there will be maybe a shift on the optimal duration of the single pulse, but the dynamical evolution of the flow field that led to obtain this maximum rate will not change. I don't think so.
Okay.
Thank you very much for your question. Thank you.
And so, since you mentioned airships in your perspective, I have to ask a few questions.
Yes, I'm not.
So if I have a few seconds, Mariana. So you mentioned CFD. I think it's an interesting problem in CFD.
Yes.
Because since you rely so much on having a proper prediction of the position of the separation point, you will be highly dependent on your model.
Yes.
So unless you go for LES or DNS, but then you will need to be a much lower Reynolds number,
yes.
And there will be a question of transfer and scaling as a function of Reynolds. So that's I think if I was still doing some research, yeah, it would be extremely interesting in tackling that problem. Sorry. Yes. So the question I had that are related to airships is that. One of the key differences that you're going to have is that so we don't have wings, we have tailplanes, and it's very low aspect ratio. So highly three-dimensional flow.
Yes.
How do you think that your work would translate in something that you know, where the flow is actually perpendicular to the leading edge? When you look at straight lines, it's something like 20% of the span, or maybe 50% of the span, but not more. Do you think that you could still achieve some kind of control, or would the flow be too complex? Would the flow be too complex to control? And the second question, so that maybe if you want to, you can do a bundle and answer to everything. It's you mentioned gust often, and here when you do your control, you have a spike in lift, but then there is something that you absolutely don't. It seems that you're not controlling it a lot. It's the relaxation time to reach something that is identical to what you have as an inlet condition. However, when you have gust, you don't control anything. You have the gust you have, so with the velocity it has, the direction it has, and the length it has. So sometimes you can get hit twice in a very short amount of time, or a very long gust, or something very short. And do you think that down the line this is something you could have some control over, meaning that the length of your controller and being able to control everything in a very short amount of times?
Okay, yes. I hope I will give a satisfactory response, but I'm not sure because I'm really not an expert. I will try to answer. Thank you, first of all, for your question. Yeah, of course, I mentioned some other possibilities of application of the fluidic actuation as we intended it over a wing. However, I believe that the perspectives that is given this work is not only something related to the wing, but is even more general a fluid mechanics problem by itself, because we are seeing that is not the response time of the actuation system that fix the rate of variation of the loads, but is the transient response of the flow to this actuation duration that fix the rate of variation of the load. So basically, if we can, I don't know how, but I think there are some possibilities to exploit the transient effects of the actuation even over other geometries, not only over a wing, because it's I think it's a fluid mechanics problem by itself. And so I believe that maybe it could be effective on other situation. Of course, when we are dealing with airfoils like helicopter rotors or blades, turbine blades, we could expect that it could give some load alleviation. However, with dirigible airships is not so easy to, but I believe that there are, if probably we can make some tests, there are some control laws that are able to increase the performance by exploiting these transient effects. And the second question is about the gust. If I well understood, is to let's say respond to a gust that you don't know a lot about it, right? You don't know what is the time scale of the gust or the
Yeah, you don't know anything.
You don't know anything. Yes, actually, this is a very, very strong question. It's very important to. It's not so easy to answer. I will try to do my best. Actually, we have seen that the single pulse actuation can lead different variation of the loads. So actually, if for example we are applying it over an airfoil, and we expect a gust, for example, and this gust, I don't know, is perpendicular to the wing, so that we reduce the angle of incidence, and so we need more lift. We say something like that. So we need more lift with a time scale which can vary depending on the strength of the gust and on the gust profile. So if we have a step or if we have a ramp, and so it will vary. I think that in this situation, if we are able to exploit a full range of duration of the actuation, so let's say, for example, we exploit from I just presented here from 0.29 to 0.86, but let's say we exploit from 0.1 to 1, and in all this actuation duration will provide a different rate of response of the lift. So I think if we are able, using pressure sensors, to capture the steady evolution of the pressure around the airfoil, we can say what is the duration of the pulse required to respond better to this particular gust that has been that wing has experienced. So I think it's not so easy as I said, but I think we can try at least to make some intelligent, smart control to calibrate the duration of the pulse in order to be able to respond to all the range of variation of the loads induced by gas. Maybe, I don't know if it can give some ideas at least of what, I don't know. I don't know if I answered, but it's not so.
No, I just wanted, yeah, we had a PhD student that defended a thesis on a gust of over an airship, and yes, it's always a very interesting question. Is you can characterize something, but what happens when you get into the real world, which is usually messier than a wind tunnel or even the CFD.
Yes.
Thank you, and thank you for your work, and congratulations.
Thank you very much. Thank you very much for your question. Thank you.
Thank you, Guillaume. Now I am inviting Dr. Jean-Pierre Rosenblum of Dassault Aviation and 3AF Association for remarks and comments and questions.
Hello, Armando. I appreciate your presentation and also your manuscript with a very good review and also a good explanation of all your work. So I had a few questions. Some were asked by Nicolas concerning the 3D effects. So I have another one concerning the Reynolds effect. How do you think the structure may evolve, or the flow topology may evolve at higher Reynolds number?
Yes. Okay. I'm not. I cannot. Thank you for the question. Actually, because it's very important, the effect of the Reynolds number. I think that for moderate Reynolds number, we will not have a very different behavior of the flow field. However, I think it can change for very high Reynolds number. And so this is a really important point, because for you, I guess, because with real aircrafts, we have Reynolds number which are much bigger than the one tested in this work. So I cannot give you let's say answer, but what I can suggest is that previous work have tested, for example, the effect of the time scales of the actuation on the optimal lift obtained. For example, I can cite the work of Seifert. They test many duration or many frequency of actuation, and at many Reynolds number, even at Reynolds number typical of aircraft, of real aircraft, and actually they were experiencing the same non-dimensional frequency, the same optimal non-dimensional frequency for all the cases. And so, independent of the Reynolds number, so they concluded that actually the transient evolution, let's say, that allows to improve the lift for this case is not so much dependent on the Reynolds number. For this reason, we just analyzed one case with the fixed Reynolds number of about 500,000. And this case was, I think it gives an idea of the dynamical evolution. However, I don't think it will change a lot by increasing the Reynolds number. If I have correctly answered to your question, I don't know. But I hope it gives some insights, because I don't think it will change a lot based on the literature I've looked at. I don't think it will change a lot by modifying the Reynolds number. At least not so much.
Okay, thank you. There was another question concerning the effect of pulse jet actuation, pulse vortex generators. In fact, what I read in your manuscript is that there are two different conclusions. If you consider either the average control or the transient effect.
Yes.
In the transient effect, it's better to have them to have the fluidic VGs far upstream from the separation line, and for the steady, the average behavior, it's better to have them close to the separation line.
Yes.
So could you explain that and comment that?
I think this is a key point, actually. Thank you very much for the question. Actually, for time averaged effects, it's better to have it not so far from the separation point, because actually with the periodic control that is always on, is always activated, we are able to reattach the flow field, even if it's closer to the separation point. However, we have seen in the transient case, we are exploiting two different dynamics if we are far upstream of the separation point and, for example, very close or even inside the separation zone. We are exploiting two different dynamics, and this can be, for example, clear by looking at this picture I presented before. For example, this one. And we see that actually if for the case when the separation operates from upstream the separated points, we have a very similar behavior at 12, 13, 14, and 13.5. But at 16 degrees, actually, when we operate from inside the separated region, we have a different behavior, because actually we are generating a very different flow dynamics response of the flow. But however, when we are in the time averaged case, our interest is to reattach the flow field, no matter what is the transient dynamical evolution of the flow field that leads to this attachment. And so, since our interest is to reattach the flow field, we are upstream, or if we are next to the separation point, we are able to reattach the flow field. And so actually this will lead to a lift increase, but we are not interested in the flow dynamical evolution that leads to this attachment. Instead, in the case of the transient evolution of the flow field, the position of the actuation, it really changes the dynamical evolution of the flow field, the consequent dynamical evolution of the flow field that is induced by the actuation onset. So I'd say there are two cases that have to be treated separately. One case is the time averaged case, when we are interested to reattach the flow field. And we have seen that the separation point upstream, the actuation just upstream of the separation point is widely known from the literature is the best. While when we are controlling the transient effects of the actuation, in this other case, we have to generate we generate two different dynamics of the flow, whether the points is upstream or inside the separation, let's say. And so we have different behavior in this case. That's why the importance of the reattachment point has not to be seen in the same view for time averaged sense and for transient in the transient case.
Yes.
If I was clear in the reply, but I was telling that it's different situations. That's why we have different results on the loads.
I was a bit surprised concerning the average reattachment, because in fact, when you try to do fluidic VGs, you have to generate your vortices, and it takes some time before they are strong enough and to interact with the mixing shear layer associated to the separation. Then if you're too close to the separation line, perhaps there will be some delay in the reattachment.
That's indeed that's what I was I actually, yes, you get the real point, because actually that's what I wanted to try to explain. Because if we are far upstream, in the case of, let's consider the case we are analyzing the transient effects of the actuation, and let's consider the case when we are far upstream of the separation point. These vortices that are created in this situation are able to fully develop before they reach the separated shear layer, so they will control very easily the separation. But if we are too close to the separation point, these vortices are very in a different flow configuration compared to the case when we have a far upstream point. And this can, for example, can be seen, I don't have the picture right now, but we can see it in the PhD dissertation, for example, by looking at figure, I give you the number of the figure, just 1 second. Yes, for example, by looking at figure 5.36 at page 124, we see that actually, if we analyze the vertical velocity in the direction over the airfoil, we see that actually, if the jets are applied at 0.3 of the chord, we will have a higher vertical velocity compared to the case when the jets are applied at 0.5 of the chord. So what does it mean? It means that in the case the jets are applied at from 0.3% of the chord, from 30% of the chord, they will this higher velocity in the downward direction will deviate this structure generated by the actuation in the downward direction, and so they will be attached to the airfoil surface. In the case when the actuators are performed from 50% of the chord instead, the vertical velocity is lower. So this structure will not remain attached to the airfoil surface. And for this reason, they are less effective in increasing in reattaching the flow field downstream. That's why in the case of the transient evolution of the flow field, the jets too close to the separation point are not so good than in the case of the time averages case. That's why, because in the time averaged case, even the jet, if they are very close to the separation point, they are still able to reattach the flow field, because we perform the actuation forever, so without interruption. And so after a certain amount of time, they will reattach the flow field. In the case of the transient effects, indeed, we perform the actuation just once, for example, and so in this case, since the jets at 0.5 are not able to completely reattach the flow over the airfoil, we will get a lower variation of the lift. So that's why it's to be interpreted in two different manners: the transient and the time averaged effects. It's two different situations. I don't know if I answered.
Yes, it explains well the fact. Concerning one last question, concerning the delta T plus variation.
Yes.
On the case of 0.86, are you sure that you don't have any bubble earlier, and that due to the limitations of PIV close to the surface, you didn't were able to measure them?
I think that if I take this case, for example, I think that in this case the bubble does not develop. Once, because in the case of the PIV measurements, they are quite close to the surface of the airfoil. I mean, the resolution, the accuracy of the PFV. The PFV is accurate in all over the field, except in a region which is a 5 millimeter height. And I don't think that in a region of this height we can have the development of a separation bubble that we didn't capture. However, I am also sure of this because I looked at the pressure variation. I don't have the picture on the slides, but in the dissertation we can compare, for example, I will not be too long in this answer, but we can compare the variation of the pressure for the case of delta T plus 0.86 with, for example, 0.46, and we notice that this negative pressure, this suction that is generated by the bubble, is not present for the case of 0.86. And so this is I'd say, this gives an idea that the bubbles is not developing in this case. And so I'm pretty sure that there is no bubble developing earlier for the case of 0.86.
And you see it on the pressure distribution for the last, since it appears at the end for this last time, which is T plus equal 2.23 or something like that. Do you see the effect of this vortex on the pressure distribution?
Yes, but I clearly don't see the development of the bubble. Yes, I think I see the actually in the case of the longer actuation duration, for example 0.86, the pressure variation is very similar to the case of the steady blowing, because we are performing the actuation for much more time, and so we don't have the formation of this bubble, and for this reason on the pressure evolution we don't obtain a region of negative pressure over the airfoil, which is associated with the development of this bubble. So since I don't see this region of negative pressure, I'm pretty sure that we didn't get the bubble earlier for the case of 0.86 and even for longer durations, because the bubble does not leave any, we don't find any signature of the bubble on the pressure evolution. So I don't think we are getting the bubble for the longer actuation duration here. We just get it very late compared to the shorter duration. But we don't get it in the phase of lift increase, just next to the phase when we obtain the maximum, but not in the phase when we increase the lift, and so this bubble will not increase the rate. So the fact that we don't have this bubble will decrease the rate.
Okay. Thank you, Armando, and congratulations.
Thank you very much. Thank you very much.
Thank you very much, Jean-Pierre. Now I'm inviting Dr. Mathieu Voisine, engineer at DGA, Direction Générale de l'Armement.
So,
Mathieu.
yeah. Thank you, Armando, for your presentation. I really appreciate, and also your manuscript.
Thank you. Thank you very much.
I just will have two questions, to be short. The first one is on your manuscript.
Yes.
You describe the phase of lift increase, and you estimate perturbation velocity.
Mm-hmm.
And I was asking if you tried to estimate this velocity with the Lyapunov exponent to see if there is a ridges, and if you can extract the velocity associated with these ridges.
Yes, thank you very much for this question. Indeed, I think this is another key point, because actually we try to estimate the velocity of the perturbation, but it's, I'd say, an average estimation. However, to be more precise, we could have used, for example, the estimation of the FTLE exponent, the finite-time Lyapunov exponent. And we tried. This is the first thing I tried. I remember it was during confinement. We were trying to process this data because the experiments were not possible, and so I tried to try to look for an integration time that was suitable to analyze the let's say the stable manifold. So in the separation point in this case, not the reattachment point, to follow the evolution of this point. And however, we had some problem because in the steady cases, it worked. It worked, and we get the same results of the streamlines. But for a steady case, with the maximum FTLE, I was getting actually I'd say the movement of the shear layer, but not the point near the surface was not moving along. It was just the maximum FTLE was just bending toward the wall, but not moving. And it was the point was expected to move. I tried with many times integration time. I get also something like 40 milliseconds backward, something like that, to try to increase the integration time, and actually the same result. However, we said this velocity yet is important because it gives an idea, but it's not the main concern, because actually we were getting we wanted the reattachment point downstream of the bubble, because this gives you the downstream movement of the bubble, and this is what we were interested in more. And for this reason, we didn't try more than this, but you're completely right. Actually, I don't know what is the problem, but we were getting some strange results from the backward FTLE analysis, and so I'm sorry, but we didn't get this velocity from this point. I don't know why. I maybe will try again, but it's strange. It's very strange. I know you are expert in this domain, but I don't know. I didn't succeed actually.
Okay. Last question. It's you did a huge work to explain the link between the bubble and the pressure coefficient.
Yes.
And you present the phase average vorticity or velocity field, and you say that you look at the instantaneous field, and did you see a variation of the lift and a different behavior on instantaneous field than on your average field?
Okay, yes. First of all, maybe let's. I want to clarify a point before to answer this question, because actually this field that we are looking is averaged, but can be considered as instantaneous because it's phase averaged. So the measurements are phase locked to the actuation signal, and so the lift that, for example, you see here in this picture is phase averaged based on many phases.
Yeah.
Actually, we can consider it as instantaneous. But if I look, I look at the evolution of the pressure. If you see, for example, this video I present here, there is in this graphic here, you see the evolution on the pressure on the suction surface of the airfoil. So this is the difference, as I said to you, between the instantaneous pressure obtained using phase average measurement, the baseline pressure coefficient, and on the bottom you see the region of FTLE of development of the bubble, and on the right you see the corresponding evolution of the lift and the derivative of the lift. So actually, if I understood clearly your question, if we now play this video, we see that actually this region of negative pressure moves downstream. As soon as this bubble moves downstream also, you can see here from this video, and actually when the bubble reaches the trailing edge, the reattachment point, you see that if I stop the video, for example, let's stop the video here, the bubble has almost reached the trailing edge, and from this moment the loads will drop compared to steady blowing. And for this reason, we are let's say this video is most explanatory of the dynamics of the flow field, because actually you see that there is a development of a region of negative pressure just below the bubble. And so I assume this bubble moves this negative pressure. Then what increases the rate of variation of the rift is the fact that the rate of variation of the pressure per unit time, so the temporal derivative of the pressure, is higher than in the case of the steady blowing. And I checked it and I compared the corresponding evolution of the bubble with the rate of variation of the pressure per unit time, so the derivative of the pressure, temporal derivative of the pressure, and I've seen that it's highly correlated, the evolution, the presence of this bubble, with a higher derivative, temporal derivative of the pressure. And so it's actually this bubble that allows to increase the rate. There is a very strong correlation between the presence of the bubble and the higher rate of lift increase, because it's associated to a higher rate of variation of the pressure per unit time.
Yeah, I think it's my fault. I want to precise on a phase average to say for example at T+1, you have a lot of different instantaneous field.
Yes.
Which give you different pressure.
Ah, yes. Okay, now I get it. Okay.
And yeah, it's the dispersion of the pressure and of the velocity field at this time.
Ah, yes. Okay.
Wait, I'm sorry.
No, I misunderstood. No, I'm sorry.
No.
I didn't understand the question. I'm sorry. And actually, your question is to correlate the bubble with the dispersion of the pressure at this instant.
If it's we see average field, you have an average evolution of the phenomenon, but I am asking if on instantaneous field, if you have a lot of differences, or if you are really close to the average field.
Okay. Well, I may answer with because when I performed the phase averaged measurements, I analyzed the dispersion in phase. So I took one phase, as you said, and analyzed the dispersion. And actually, what I found is that the dispersion is not so high. Actually, I'd say surprisingly is not so high. And so, especially for these 14 degrees incidences, we had very, very small differences between every phase. And so dispersion was too low that actually I think that the phase averaged measurements that I plot here are really representative of the unsteady behavior of the flow field, even considering the dispersion of measurements for each phase. So okay. I think if I take one phase and I plot it against the phase average measurement that I show here, if I take just one phase, we will get with the 5% error, we will get the same evolution. And so this is so the phase average measurement that we get are very representative of the real behavior of the flow. I checked it in detail before doing phase average, and yes, if I don't know if I answered, but yes, it's representative.
Okay, thank you again, Armando.
Thank you very much, Mathieu, for your question.
Thank you, Mathieu. Now it is my turn to make some comments and ask maybe 1-2 questions. First of all, Armando, I congratulate you for the clarity of your presentation. I liked it very much, and I found that your thesis gives a special light of how the coherent vortex structures are manipulated through these kinds of actuations towards increase of the benefits and the performances, and not only concerning the forces, but also the gradients of the forces and the pressure derivatives. So to me, it gives a significant contribution for other and future methods of control and manipulation of the structures around a wing towards increased efficiency. And concerning this, I have to say I find that your thesis brings an important contribution. A second important contribution, as also was pointed out in the reviews of the two reviewers, of course, is chapter 5, the transient effects analysis, which is quite an original aspect in the state of the art. Now, I would ask a question. You, in several parts of the thesis, you present many times, of course, you present a lift, and several times you present the pressure drag. I know from own experience in our group, it is more difficult to measure the drag contribution, of course. But it would be helpful if systematically you present the lift to drag, the aerodynamic efficiency,
yes,
systematically, because we sometimes see indeed that we have an increase of lift. But as we know, when you create these beneficial bubbles, as you show, the vortices, these vortex bubbles, you at the same time increase the thickness of the so-called effective aerodynamic obstacle, which includes the viscous area and goes up to the so-called turbulent, non-turbulent interface. So benefits of lift can have to be investigated if they don't rise so much the drag in the same time. And at the end of the story, if you have, however, a lift over D increased, even if you increased a little bit the drag, it is interesting for the design anyway.
Yes.
So this is my remark. Yes. Now, you had presented, I think, in Transparency 46, you said that the drag decreases in high incidence. You said so, I think.
46, just...
46, should I not note exactly? Well, at the moment, you said that you have also a decrease of drag in high incidence.
Yes.
Maybe I did not note exactly the number of the transparency. I'm sorry.
So this one, I think, is this one.
Yes.
Is this one, Professor?
Yes.
Oh,
yes.
Okay. Okay.
So you say that for the high incidences, you obtained a decrease, as we see,
yes.
Of the drag.
Yes.
Can you explain physically how this is achieved? This is very important.
Of course.
No.
I expected this question because it's a very important question, I think. For this reason, I prepared a special slide. I hope I will find it. First of all, it's the first thing to find this slide. Just 1 second. Yes, this one. Okay. Now, if you look at this slide, actually, this is not so, I'd say, I will present it very, very fast because it's getting late. And my advisor also tells it's getting late. So I will try to present it very fast. So actually, if you take, for example, the quarter chord and we applied the total aerodynamic force in this point, we can decompose this force into the body reference system, obtaining T and N. And so we can write the coefficient of the force as the square root of Cn squared plus Tt squared. So if we now want to get the drag, the pressure drag is basically what? The square root of the Cn square plus Ct square for what? The sinus of the angle alpha, that is the incidence, minus the angle theta, which is the angle between the normal to the chord and the force direction. So I say all this, so if we retain the second expression, let's retain CdP equal to square root of Cn square plus Ct square for sinus alpha minus theta. Now let's compare the two cases at 14 and 16 degrees. So at 14 degrees, actually, what happens is that the actuation is able to increase the modulus of the force because it induces a suction over the upper surface of the airfoil. However, since we have a moderate suction near the leading edge, it's not able to bend this vector. Indeed, if I make a zoom, I don't know if I can, but we see that the vectors, black and the red one, are almost parallel. So the angle theta is not changing. So what we increase is just the modulus, and then when we calculate the pressure drag, we have an increasing modulus, but not we don't have a variation of the angle. And so actually we increase the drag. The opposite is instead obtained at 16 degrees, where instead we increase, of course, the modulus, but since we have a stronger suction near the leading edge, we also increase the angle theta, and so the sinus of alpha minus theta will outweigh the increase of modulus and lead to a drag decrease. So this is from a mathematical point of view, but from a physical point of view, how we can interpret this? We can interpret this that in the case of 16 degrees, since we have a stronger suction near the leading edge, we are actually pulling the airfoil in the upstream direction, and so this helps to decrease the drag, and indeed we obtain a drag decrease. For 14 degrees instead, the predominant phenomenon is the suction near the half chord, which actually helps to pull the airfoil in the downstream direction. And this also corresponds to a drag increase. That's why we have a strong different behavior. And the key point to understand this different behavior is that at 16 degrees, we are able to bend the aerodynamic force resultant and so to generate a drag decrease.
Okay, this is a very important effect, very, very good explanation. Thank you very much. I have a last question. The Reynolds number range where you worked, I think for the wings of this kind corresponds to, don't you have transition to turbulence effects in the upstream region? Or the boundary layer is always turbulent from the beginning?
Yes, for this reason we had a small recirculation bubble near the leading edge because the boundary layer was initially laminar and then it became turbulent, and so we had this small recirculation bubble. We didn't want this. We wanted a fully turbulent flow field over the airfoil that could ensure a separation from the trailing edge. And so for this reason, we tripped the boundary layer using a carborundum band just downstream of the leading edge in order to suppress the presence of this recirculation bubble and to obtain a fully turbulent flow. So yes, it's true that with this Reynolds range, we have a laminar behavior near the leading edge, but we tripped it, and so we had a fully turbulent flow.
I think I have a networks problem. Can you hear me?
Yes, we can hear.
Yes. Okay, I understand. So you tripped because an interesting issue is how these jets, this kind of actuators would affect the transition area and how the result would be affected by modifying the transition area. It can be an problem of investigation in this Reynolds number range.
Yes, actually, I'm honest to say that we did not investigate the effect of the actuators on the transition but it was investigated by some old studies that were carried out in the same wind tunnel in 2006 by Bourgois, and they actually performed actuation both over naturally transition boundary layer and on triggered transition boundary layer. So actually compared both evolution of the lift for these two cases, and yes, he found that if I'm not wrong, but because I didn't remember very well the results, but the difference in the evolution of the lift for these two cases was not so different. Of course, there was a difference in the magnitude of the maximum lift, but the say the physical phenomena that were expected were not so different between these two cases, because with the actuators in place, I think we promote transition, and so even if we don't have natural transition, by using actuation we are able to create transition in the boundary layer, and actually we will fall in the same situation where we have already transition. So the results are, yes, of course different, but not so much to explain a really different dynamical behavior of the flow.
Okay, thank you very much for your answer. Now I am inviting Dr. Jean-Paul Dussoge, Director of Research CNRS at P', co-director of the thesis, for remarks and comments. Jean-Paul?
Yes. To be clear, I'm not Jean-Paul Dussoge, I am Jean-Paul Bonnet.
Oh, Jean-Paul. Sorry, Jean-Paul, definitely.
Jean-Paul Dussoge is a good friend of me.
Yes, sure, sorry. May I make a comment? I had yesterday, late afternoon, my second vaccination of COVID-19 by Pfizer, and I must accept that I am a bit ill since yesterday evening and all the day today. So sorry for the lapsus.
There is no problem, Marina. I hope you will recover very soon.
I hope. Thank you. Please go ahead.
Yeah, so just a few words about my role in this thesis. So this is very interesting to see that initially we start with a study that was developed by Wei Long, maybe 10 years ago around. And at that time, we were entirely focused on the turbulence behavior and mainly of the wake itself. Because in my spirit, the idea was to look at the behavior of the turbulence that is, let's say, concerned by rapid evolution, and so to know how the turbulence reacts itself. And so we had some, let's say, room left after this thesis about the physical of the mechanism. And what was very interesting is to see that Armando and Christophe and Jacques, they take care of the old experiment and they change the view of that by completing this for a real aerodynamic study of all the process. And I can say that even the turbulence is a complex phenomena by itself, the scales and the dynamic of the scales, the interaction of scales and so on. The entire problem of the separation and the lift and the drag associated with the separation is maybe more complex indeed, and requires so many subtle measurements that I am very, let's say, happy to see how they change the point of view, starting with this turbulence behavior, going to the entire mechanism. And so indeed, I have no question. I was very, maybe I have one, but let's say Armando is a bit late. I am very happy and to see how many results are produced and so on. Maybe just, we will discuss this later on, but this is in the spirit of Mariana's question. So the question is, what is the role of the turbulence itself in the typical scales? And maybe this is another thesis that can be performed. What, in a few words?
Yes.
Armando, please.
Yes, it's not very. Thank you for your question, Jean-Paul, and for your appreciation. Jean-Paul actually followed our work from in details because he came a lot of times to give us useful advice for our experiments, and so I would like to thank you for this. And he also actively participated in the advancement of the work. To respond to this question, I'm not sure if maybe Jack can give a better response of the turbulence scales in play in this behavior. But I think that for 1 second we could let's say analyze the phenomenon from a global view and say that if there are many ways of perturbing the flow. We can perturb the flow at scales of the global instability of the flow over the airfoil. We can perturb the flow at the stability, so at the scales of the separated shear layer, and we can obtain different results. Because it's true that the turbulence in the near wake is coupled with the scales of the separated shear layer, but they're not the same frequency. And so this is already a question. So what is the best frequency of perturbation? What is the best scales to be excited in order to obtain the best improvement of the lift? And actually there are many studies of this. And however, I believe that in our case, this reasoning is pertinent, but it goes let's say in a not opposite, but in a different sense, because didn't want to explore the effect of the actuation frequency on the turbulence scales of the phenomenon. Indeed, what we wanted to understand is the effects of even a short actuation pulse on the global dynamics of the flow. So I cannot give you an answer because our kind of actuation was not periodic, and so we didn't excite any frequency, neither the one of the global instability, neither the one of the shear layer. However, we played over the global dynamics of the flow. And so it can be seen this other way, let's say like that. I just turned a bit your question, I'm sorry, Jean-Paul, but I hope I give you an idea that is important to understand to understand what is the frequency of actuation that excites more efficiently the shear layer. This is very, very important, and it has been a wide object of study. And Professor Gleiser can say this, but also you, Jean-Paul, that worked in this field for many years. However, I think in our particular approach, we didn't focus too much on the effective scales of actuation, but we focus on the effect on the global dynamic evolution of the field. So it's we turned into a more aerodynamic approach of the problem.
Okay, thank you very much, and congratulations for suffering 3, let's say, coaches during your thesis. It's not obvious.
Yes, no, it's a pleasure. It's a pleasure. Thank you very much, Jean-Paul.
Thank you, Jean-Paul. Thanks so much. Now I am inviting Professor Jacques Borret, co-director of this thesis, for comments, questions. Jacques?
Yes, thank you very much. Thank you very much. Mariana. Il n'y a pas d'écho.
I removed.
Okay. Thank you very much, Mariana. So, I don't have any questions, of course. I want I will let Christophe comment about the physics. And just I want to congratulate Armando for his work, for his defense, and also his courage. I just want to say, for example, that the work with FTLE was made during the confinement, and the very hard confinement last year, at the beginning, the first one. So everybody was at home. Armando was not in a comfortable home, and he had the courage to work on his own PC to analyze this data, and we were exchanging a lot with him at that time. So it gives an example of his also strength of character. Thank you for all the committee. Maybe I will play this role because I'm the official director. And thank you for all the committee to accepted to be with us this evening. Thank you very much, Mariana, because it's not easy, this vaccination, and thank you very much for being accepted to be president in this difficult condition. I have exchanged a little with Professor Glaser because he left us. Maybe we could speak in French, by the way, but about FTLE, and so I won't make a reply to Professor Glaser about FTLE, but he's asking very nice questions about the use of this tool. And of course, we wanted to have in this committee also Jean-Pierre, who is from Dassault and very involved in all the controls since a long time. And we wanted to have Guillaume also because of we were thinking that maybe during the transient maneuvers, even if it is maybe optimistic, playing with the separated flow might give some degrees of freedom to act on the dirigeable. So, but this maybe we would require more discussion. It was really a nice period to work together on these problems. And thanks Jean-Paul also for helping us at the beginning. And it's very strange for us because we are really in the room where most of the discussions took place. So the defense is really in the same place. And Armando was always very enthusiastic. So I thank you very much for being here on Friday evening so late. And I thank you, Mariana, and I give back the speech to you.
Thank you very much, Jacques. Last but not least, I'm inviting Dr. Christophe Sicot, maître de conférence and co-director of the thesis for remarks and comments. Christophe.
Okay, thank you, Mariana. Just a few words in English for maybe Armando's families after I will go on in French. Yes, I have no question because Armando respond communication today, and I congratulate him for this.
Thank you.
Yes, I would like to first congratulate Armando for his work. Always smile because we work together from 4 years now. And it was difficult to start because for us it was the beginning of experiments. It was difficult to start with experiments. And Armando try and reach a dream with us. Congratulations for this.
Thank you very much.
Maybe in France now, I know that unfortunately Professor Glaser left us. Je voulais rejoindre en premier à Jacques pour remercier tout le jury. Dans des conditions difficiles à cette heure tardive, pour avoir commenté ce travail, questionné énormément avec des questions très pertinentes qui ouvrent de nombreuses autres questions, particulièrement Mariana, dans ces conditions difficiles. Merci beaucoup. Je voulais aussi remercier, parce que, comme je l'ai dit, Armando est arrivé sur une nouvelle expérience et un très gros travail expérimental pour nous. Et je vais en profiter pour remercier toute l'équipe technique qui a supporté Armando, en particulier Jean-Marc, supporté dans tous les sens du terme. Donc voilà, merci pour tout. Et je remercie à nouveau Armando en français, puisque ça a été un réel plaisir de travailler avec lui.
Merci beaucoup.
Durant cette période.
Merci beaucoup, Christophe, c'est un plaisir pour moi aussi.
Même si le travail a parfois été difficile, effectivement, avec le confinement. Voilà, merci beaucoup. Juste quelques mots, enfin je le cite encore, et juste quelques mots sur les questions que vous avez pu poser en étant très rapide parce qu'il est tard. Je pense qu'effectivement, le travail d'Armando nous a ouvert beaucoup de perspectives parce qu'il aussi, il a creusé beaucoup de choses. On a encore une grosse base de données qu'on a peut utiliser. Et je pense que pour nous, ça va être très important, le travail d'Armando, parce que on l'a vu, et Armando a répondu aux différentes questions, en particulier celle de Guillaume sur futures applications et d'autres applications. Donc, je pense qu'effectivement, on touche là le cœur du sujet. Comment on peut contrôler cette zone décollée et des zones non décollées avec ce type d'actuation. Je pense que le champ des possibles est très grand et que le travail, que ce soit sur des profils d'aile ou d'autres formes, ou d'autres objets, en particulier les drones ou les dirigeables, ouvre des perspectives vraiment intéressantes pour notre laboratoire. Et grâce à Armando, on a pu aller assez loin dans ce premier travail pour justement être assez couchant sur le fait qu'il y a un réel intérêt à contrôler par ces phénomènes transitoires toutes les régions décollées. Voilà, je vais pas être beaucoup plus long. Je remercie et je félicite encore Armando pour ton travail. Je sais qu'on a encore beaucoup de travail à faire ensemble, donc je m'en félicite par avance. On n'a pas encore tout fait, mais bonne chance pour la suite. Merci beaucoup au jury et je donne la parole à Mariana.
Bien, merci Christophe. Merci à tout le jury pour votre commentaire et participation. Now we will leave from this room and the jury will connect to the jury's room for the deliberation, and then we will come back to this room for the final result. Okay?
Okay.
So,
thank you very much.
I am disconnecting myself.
See you.
Peut-être que le plus simple, Armando,
Armando? Ça vient, ça vient. Mets-toi en place, mets-toi en place. Écoute, c'était très bien, mais il faudrait que tu apprennes à faire des réponses plus courtes. Hein? J'ai jamais vu une durée de thèse aussi longue. Mais c'était bien. Bravo. Non, c'était bien. Bon, alors, pourquoi ils viennent pas les autres? Ah, voilà Nicolas. Voilà Mathieu. Jean-Pierre. Salut Jean-Pierre. On ne se pas saluer directement.
Ça a été rude.
Ouais, ça a été rude. Jean-Pierre, tout va bien pour toi?
Ton micro est coupé, Jean-Pierre.
Oui, ça va. Ça va, Jean-Paul. Bonjour.
Ça va, tu t'es bien remis, tout va bien.
Oui, oui.
Bon. Bon, Armando, you can stay. We cannot see you due to the camera, but okay. I will. Le jury, là, je peux parler en français. Nous sommes. OK. Bon, Armando CARUSONE, le jury a délibéré suite à votre défense de thèse. Vous avez fait une présentation très claire et pédagogique, reflétant la haute qualité du travail accompli par rapport à une problématique complexe du contrôle des écoulements. Vous avez mis en évidence des aspects à la fois très fondamentaux ainsi que des aspects applicatifs pour le domaine de l'aéronautique et les moyens de contrôle pour améliorer les performances aérodynamiques. Vous avez très bien répondu aux questions qui ont bien clarifié les phénomènes étudiés. Il faut dire que vous avez eu de nombreuses questions et vous avez su donner des réponses complémentaires par rapport aux explications et descriptions des différents aspects dans votre manuscrit, ouvrant ainsi la voie vers de futures études en aérodynamique stationnaire du transport dans plusieurs domaines. Vous avez fait preuve de recul par rapport à votre sujet de thèse et vous avez anticipé pas mal de questions posées. Vous avez été bien préparé, on a trouvé. De par votre support de présentation, vous avez fait preuve d'une pédagogie dynamique et nous avons bien apprécié cet aspect-là tout au long de votre présentation qui nous a été donc donné et qui a été très très clair. Pour l'ensemble de ces raisons, le jury à l'unanimité a décidé de vous décerner le grade de docteur de l'École nationale supérieure de mécanique et d'aérothermique et nous ajoutons toutes nos félicitations.
Merci beaucoup. I would like to thank every.
Et tu peux parler en français parce que.
Ah, yes, oui. On
parle your family on your colleagues.
Ah oui, pardon.
Non, on peut parler en français. Oui, en français après. Oui, je voudrais vous remercier pour votre présence ici, même si c'est très tard. Et en fait, je voudrais vous remercier pour vos commentaires sur mon sujet de thèse qui ont donné de l'inspiration pour des autres perspectives de ce travail. Je voudrais aussi remercier mes superviseurs qui sont là avec moi jusqu'à 9h le soir, en particulier avec Christophe et Jacques. Je voudrais le remercier pour leur support pendant tout on peut dire mon travail à l'ENSMA. Je suis arrivé comme stagiaire et après j'ai continué avec une thèse. Grâce à eux, je suis parti de zéro et j'espère d'avoir donné un apport à la communauté sur ces sujets. Donc, merci vraiment beaucoup à mes superviseurs et merci beaucoup à les autres membres du jury. And thank you very much to all people for doing this presentation.
Ok. Bon. On va te dire comme ça avec le coup. Pour marquer quand même le coup. Merci beaucoup. Ce qui est triste après, c'est qu'on ne peut pas boire virtuellement ensemble. Ah oui, c'est là, je vais bouger. Merci beaucoup. Oui, ce qui est triste, c'est qu'on ne peut pas prendre un pot virtuellement ensemble. Même à l'ANSMA, c'est interdit formellement de prendre un pot. Bon. Comme c'est vendredi soir, je ne sais pas ce qu'on va faire, mais bon. Enfin bon. Merci beaucoup pour être resté aussi tard. C'est la première fois que je fais une thèse à 9h du soir quand même aussi. Il fallait attendre Armando pour arriver là. Et j'espère vous revoir bientôt en chair et en os à de multiples occasions et au laboratoire ou dans les laboratoires ou les lieux respectifs où vous êtes. Donc merci aussi pour tout le travail de lecture, de rapport. Je sais que c'est du temps et que tout le monde est bien occupé. Voilà.
Merci beaucoup à tous. J'ajoute pas grand-chose. Merci.
Bien, félicitations Armando et je vous souhaite une brillante carrière. Et les félicitations vont aussi au co-encadrant, co-directeur de cette thèse. Et encore une fois, j'ai eu l'occasion de constater l'excellence, bien sûr, des thèses menées à P'. Et merci beaucoup au co-directeur de thèse pour l'aimable invitation à ce jury. Voilà, et je vous souhaite à tous une bonne soirée et bon week-end.
Merci Mariana. On oublie.
Au revoir Mariana.
Qui a toujours été là aussi.
L'équipe qui est à l'origine du projet.
Qui était à l'origine du projet.
Oui, c'est vrai, c'est important.
Bon.
Au revoir.
Au revoir à tous.
Au revoir.
Merci.
Félicitations.
Félicitations, oui.
Merci.
Armando.
Bravo. Et bon courage pour la suite.
Merci. Merci beaucoup, Nicolas. Merci.
Oui, on aura peut-être l'occasion de se revoir.
Oui, bien sûr. Oui.
Allez, bonne soirée à tous.
La prochaine conférence.
Allez, bonne soirée.
Au revoir.
Au revoir.
Au revoir.
C'est bien que Jean-Paul ait quitté plus tôt.
Oui.
C'était déconnecté plus tôt.
Oui, c'était connecté tout le temps.
Du coup, c'était fini.
Ok.
Bon, bah là, c'est fini pour les deux.
Je vais continuer à enregistrer. Ouais, j'ai